Chapter 7, Section I Airplane Basic Flight Maneuvers Using Analog Instrumentation. Introduction. Instrument flying techniques differ according to aircraft type, class, performance capability, and instrumentation. Therefore, the procedures and techniques that follow need to be modified to suit individual aircraft. Recommended procedures, performance data, operating limitations, and flight characteristics of a particular aircraft are available in the Pilot's Operating Handbook/Airplane Flight Manual, PO/AFM, for study before practicing the flight maneuvers. The flight maneuvers discussed in Chapter 7 I assume the use of a single-engine, propeller-driven small airplane with retractable gear and flaps and a panel with instruments representative of those discussed earlier in Chapter 5, Flight Instruments. With the exception of the instrument takeoff, all of the maneuvers can be performed on partial panel, with the attitude gyro and heading indicator covered or inoperative. Straight and level flight pitch control. The pitch attitude of an airplane is the angle between the longitudinal axis of the airplane and the actual horizon. In level flight, the pitch attitude varies with airspeed and load. For training purposes, the latter factor can normally be disregarded in small airplanes. At a constant airspeed, there is only one specific pitch attitude for level flight. At slow cruise speeds, the level flight attitude is nose high with indications as in Figure 7.1. At fast cruise speeds, the level flight attitude is nose low. Figure 7.2, Figure 7.3 shows the indications for the attitude at normal cruise speeds. The instruments used to determine the pitch attitude of the aircraft are the attitude indicator, the altimeter, the vertical speed indicator, VSI, and the airspeed indicator, ASI. Attitude indicator. The attitude indicator gives the direct indication of pitch attitude. The desired pitch attitude is gained by using the elevator control to raise or lower the miniature aircraft in relation to the horizon bar. This corresponds to the way pitch attitude is adjusted in visual flight by raising or lowering the nose of the airplane in relation to the natural horizon. However, unless the airspeed is constant, and until the level flight attitude for that airspeed has been identified and established, there is no way to know whether level flight as indicated on the attitude indicator is resulting in level flight as shown on the altimeter, VSI, and AC. If the miniature aircraft of the attitude indicator is properly adjusted on the ground before takeoff, it shows approximately level flight at normal cruise speed when the pilot completes the level off from a climb. If further adjustment of the miniature aircraft is necessary, the other pitch instruments must be used to maintain level flight while the adjustment is made. To practice pitch control for level flight using only the attitude indicator, use the following exercise. Restrict the displacement of the horizon bar to a 1/2 bar width, a bar width up or down, then a 1 1/2 bar width. 1/2, 1 and 1 1/2 bar width nose high attitudes are shown in Figures 7-4, 7-5, and 7-6. An instructor pilot can demonstrate these normal pitch corrections and compare the indications on the attitude indicator with the airplane's position to the natural horizon. Pitch attitude changes for corrections to level flight by reference to instruments are much smaller than those commonly used for visual flight. With the airplane correctly trimmed for level flight, the elevator displacement, and the control pressures necessary to effect these standard pitch changes are usually very slight. The following are a few helpful hints to help determine how much elevator control pressure is required. First, a tight grip on the controls makes it difficult to feel control pressure changes. Relaxing and learning to control the aircraft usually takes considerable conscious effort during the early stages of instrument training. Second, make smooth and small pitch changes with positive pressure. With practice, a pilot can make these small pitch corrections up or down, freezing, holding constant, the 1/2 full and 1 1/2 bar widths on the attitude indicator. Third, with the airplane properly trimmed for level flight, momentarily release all pressure on the elevator control when becoming aware of tenseness. This is a reminder that the airplane is stable, except under turbulent conditions. It maintains level flight if left alone. Even when no control change is called for, it is difficult to resist the impulse to move the controls. This may be one of the most difficult initial training problems in instrument flight. Altimeter at constant power, any deviation from level flight, except in turbulent air, is the result of a pitch change. Therefore, the altimeter gives an indirect indication of the pitch attitude in level flight, assuming constant power. Since the altitude should remain constant when the airplane is in level flight, any deviation from the desired altitude signals the need for a pitch change. If the aircraft is gaining altitude, the nose must be lowered. Figures 7-7 and 7-8, the rate of movement of the altimeter needle is as important as its direction of movement in maintaining level flight without the use of the attitude indicator. An excessive pitch deviation from level flight results in a relatively rapid change of altitude. A slight pitch deviation causes a slow change. Thus, if the altimeter needle moves rapidly clockwise, assume a considerable nose-high deviation from level flight attitude. Conversely, if the needle moves slowly counterclockwise to indicate a slightly nose-low attitude, assume that the pitch correction necessary to regain the desired altitude is small. As the altimeter is added to the attitude indicator in a cross-check, a pilot learns to recognize the rate of movement of the altimeter needle for a given pitch change as shown on the attitude indicator. To practice precision control of pitch in an airplane without an attitude indicator, make small pitch changes by visual reference to the natural horizon and note the rate of movement of the altimeter. Note what amount of pitch change gives the slowest steady rate of change on the altimeter. Then practice small pitch corrections by accurately interpreting and controlling the rate of needle movement. An instructor pilot can demonstrate an excessive nose-down deviation, indicated by rapid movement of the altimeter needle, and then, as an example, show the result of improper corrective technique. The normal impulse is to make a large pitch correction in a hurry, but this inevitably leads to over-controlling. The needle slows down, then reverses direction, and finally indicates an excessive nose-high deviation. The result is tension on the controls, erratic control response, and increasingly extreme control movements. The correct technique, which is slower and smoother, returns the airplane to the desired attitude more quickly, with positive control and no confusion. When a pitch error is detected, corrective action should be taken promptly, but with light control pressures and two distinct changes of attitude: 1. A change of attitude to stop the needle movement, and 2. A change of attitude to return to the desired altitude. When the altimeter indicates an altitude deviation, apply just enough elevator pressure to decrease the rate of needle movement. If it slows down abruptly, ease off some of the pressure until the needle continues to move, but ease off slowly. Slow needle movement means the airplane attitude is close to level flight. Add slightly more corrective pressure to stop the direction of needle movement. At this point, level flight is achieved. A reversal of needle movement means the aircraft has passed through it. Relax control pressures carefully, continuing to cross-check since changing airspeed causes changes in the effectiveness of a given control pressure. Next, adjust the pitch attitude with elevator pressure for the rate of change of altimeter needle movement that is correlated with normal pitch corrections, and return to the desired altitude. As a rule of thumb, for errors of less than 100 feet, use a half-bar width correction. Figures 7 to 9 and 7 to 10, for errors in excess of 100 feet, use an initial full bar width correction. Figures 7 to 11 and 7 to 2012, practice predetermined altitude changes using the altimeter alone, then in combination with the attitude indicator. Vertical speed indicator, VSI. The VSI, like the altimeter, gives an indirect indication of pitch attitude and is both a trend and a rate instrument. As a trend instrument, it shows immediately the initial vertical movement of the airplane, which, disregarding turbulence, can be considered a reflection of pitch change. To maintain level flight, use the VSI in conjunction with the altimeter and attitude indicator. Note any positive or negative trend of the needle from zero and apply a very light corrective elevator. To correct altitude error. Correction initially. Pressure. As the needle returns to zero, relax the corrective pressure. If control pressures have been smooth and light, the needle reacts immediately and slowly, and the altimeter shows little or no change of altitude. As a rate instrument, the VSI requires consideration of lag characteristics. Lag refers to the delay involved before the needle attains a stable indication following a pitch change. Lag is directly proportional to the speed and magnitude of a pitch change. If a slow, smooth pitch change is initiated, the needle moves with minimum lag to a point of deflection corresponding to the extent of the pitch change, and then stabilizes as the aerodynamic forces are balanced in the climb or descent. A large and abrupt pitch change produces erratic needle movement, a reverse indication, and introduces greater time delay lag before the needle stabilizes. Pilots are cautioned not to chase the needle when flight through turbulent conditions produces erratic needle movements. The apparent lag in airspeed indications with pitch changes varies greatly among different airplanes and is due to the time required for the airplane to accelerate or decelerate when the pitch attitude is changed. There is no appreciable lag due to the construction or operation of the instrument. Small pitch changes, smoothly executed, result in an immediate change of airspeed. When using the VSI as a rate instrument and combining it with the altimeter and attitude indicator to maintain level flight, a pilot should know that the amount the altimeter needle moves from the desired altitude governs the rate that should be used to return to that altitude. A rule of thumb is to make an attitude change that results in a vertical speed rate approximately double the error in altitude. For example, if altitude is off by 100 feet, the rate of return to the desired altitude should be approximately 200 feet per minute, FPM. If it is off by more than 100 feet, the correction should be correspondingly greater, but should never exceed the optimum rate of climb or descent for the airplane at a given airspeed and configuration. A deviation of more than 200 FPM from the desired rate of return is considered over-controlling. For example, if attempting to change altitude by 200 feet, a rate in excess of 400 FPM indicates over-controlling. When returning to an altitude, the VSI is the primary pitch instrument. Occasionally, the VSI is slightly out of calibration and may indicate a climb or descent when the airplane is in level flight. If the instrument cannot be adjusted, take the error into consideration when using it for pitch control. 4. Example: if the needle indicates a descent of 200 FPM while in level flight, use this indication as the zero position. Airspeed indicator, ASI, the ASI presents an indirect indication of the pitch attitude. In non-turbulent conditions with a constant power setting and pitch attitude, airspeed remains constant. Figure 7.13, as the pitch attitude lowers, airspeed increases, and the nose should be raised. Figure 7.14, as the pitch attitude rises, airspeed decreases, and the nose should be lowered. Figure 7.15, a rapid change in airspeed indicates a large pitch change, and a slow change of airspeed indicates a small pitch change. Constant airspeed, constant pitch. Figure 7.13. Constant power plus constant pitch equals constant speed. Increased airspeed, decreased pitch. Figure 5.14. Constant power plus decreased pitch equals increased airspeed. Figure 7.14. Constant power plus decreased pitch equals decreased airspeed, increased pitch. Figure 5.15. Constant power plus increased pitch equals decreased airspeed. Figure 7.15. Constant power plus increased pitch equals decreased airspeed. Pitch control in level flight is a question of cross-check and interpretation of the instrument panel for the instrument information that enables a pilot to visualize and control pitch attitude. Regardless of individual differences in cross-check technique, all pilots should use the instruments that give the best information for controlling the airplane in any given maneuver. Pilots should also check the other instruments to aid in maintaining the primary instruments at the desired indication. As noted previously, the primary instrument is the one that gives the most pertinent information for a particular maneuver. It is usually the one that should be held at a constant indication. Which instrument is primary for pitch control in level flight, for example? This question should be considered in the context of specific airplane, weather conditions, pilot experience, operational conditions, and other factors. Attitude changes must be detected and interpreted instantly for immediate control action in high-performance airplanes. On the other hand, a reasonably proficient instrument pilot in a slower airplane may rely more on the altimeter for primary pitch information, especially if it is determined that too much reliance on the attitude indicator fails to provide the necessary precise attitude information. Whether the pilot decides to regard the altimeter or the attitude indicator as primary depends on which approach will best help control the attitude. In this handbook, the altimeter is normally considered as the primary pitch instrument during level flight. Bank control. The bank attitude of an airplane is the angle between the airplane's wings and the natural horizon. To maintain a straight and level flight path, the wings of the airplane are kept level with the horizon, assuming the airplane is in coordinated flight. The instruments used for bank control are the attitude indicator, the heading indicator, and the turn coordinator. Figure 7.16 illustrates coordinated flight. The aircraft is bank left with the attitude indicator and turn coordinator indicating the bank. The heading indicator indicates a left turn by apparent clockwise rotation of the compass card behind the airplane silhouette. Attitude indicator. The attitude indicator shows any change in bank attitude directly and instantly and is, therefore, a direct indicator. On the standard attitude indicator, the angle of bank is shown pictorially by the relationship of the miniature aircraft to the artificial horizon bar and by the alignment of the pointer with the banking scale at the top of the instrument. On the face of the standard 3-inch instrument, small angles of bank can be difficult to detect by reference to the miniature aircraft, especially if leaning to one side or changing a seating position. Precession error. Small deviations from straight coordinated flight can be readily detected on the scale pointer. The banking index may be graduated as shown in Figure 7.17, or it may be graduated in 30 degrees increments. The instrument depicted in Figure 7.17 has a scale pointer that moves in the same direction of bank shown by the miniature aircraft. In this case, the aircraft is in a left 15 degrees bank. Precession errors in this instrument are common and predictable, but the obvious advantage of the attitude indicator is an immediate indication of both pitch attitude and bank attitude in a single glance. Even with the precession errors associated with many attitude indicators, the quick attitude presentation requires less visual effort and time for positive control than other flight instruments. Heading indicator. The bank attitude of an aircraft in coordinated flight is shown indirectly on the heading indicator, since banking results in a turn and change in heading. Assuming the same airspeed in both instances, a rapid movement of the heading indicator, azimuth card in a directional gyro, indicates a large angle of bank, whereas slow movement reflects a small angle of bank. Note the rate of movement of the heading indicator and compare it to the attitude indicator's degrees of bank. The attitude indicator's precession error makes a precise check of heading information necessary in order to maintain straight flight. When deviations from straight flight are noted on the heading indicator, correct to the desired heading using a bank angle no greater than the number of degrees to be turned. In any case, limit bank corrections to a bank angle no greater than that required for a standard rate turn. Use of larger bank angles requires a very high level of proficiency, and normally results in over-controlling and erratic bank control. Turn coordinator. The miniature aircraft of the turn coordinator gives an indirect indication of the bank attitude of the airplane. When the miniature aircraft is level, the airplane is in straight flight. When the miniature airplane is aligned with one of the alignment marks and the aircraft is rolling to the left or right, the indication represents the roll rate, with the alignment marks indicating a roll of 3 degrees per second in the direction of the miniature aircraft. This can be seen in level flight when a bank is introduced either to the left or the right. The turn coordinator's indicator will indicate the rolling motion although there is no turn being made. Conversely, a pedal input to the right or left causes the aircraft to turn momentarily about its vertical axis, with no rolling motion, with an indication of turn on the turn coordinator. After the turn becomes stabilized and the aircraft is no longer rolling, the turn coordinator displays the rate of turn with the alignment marks equaling a turn of 3 degrees per second. The turn coordinator is able to display both roll and turn parameters because its electrically powered gyroscope is canted at an angle. As a result, the turn and slip indicator provides both roll and turn indications. Autopilots in general aviation today use this instrument in determining both roll and turn information. After the completion of a turn, return to straight flight is accomplished by coordinated aileron and rudder pressure to level the miniature aircraft. Include the miniature aircraft in the cross-check and correct for even the smallest deviations from the desired position. When this instrument is used to maintain straight flight, control pressures must be applied very lightly and smoothly. The ball of the turn coordinator is actually a separate instrument, conveniently located under the miniature aircraft because the two instruments are used together. The ball instrument indicates the quality of the turn. If the ball is off-center, the airplane is slipping or skidding. That is, if the coordinator's miniature airplane is tilted left and the ball is displaced to the right, the aircraft is in a skid. Figure 7.18, if however, the miniature airplane is tilted to the right with the ball off-center to the right, the aircraft is in a slip. Figure 7.19, if the wings are level and the airplane is properly trimmed, the ball remains in the center, and the airplane is in straight flight. If the ball is not centered, the airplane is improperly trimmed. To maintain straight and level flight with proper trim, note the direction of ball displacement. If the ball is to the left of center and the left wing is low, apply left rudder pressure to center the ball and correct the slip. At the same time, apply right aileron pressure as necessary to level the wings, cross-checking the heading indicator and attitude indicator while centering the ball. If the wings are level and the ball is displaced from the center, the airplane is skidding. Note the direction of ball displacement, and use the same corrective technique as for an indicated slip. Center the ball, left ball/left rudder, right ball/right rudder, use aileron as necessary for bank control and retrim. To trim the airplane using only the turn coordinator, use aileron pressure to level the miniature aircraft and rudder pressure to center the ball. Hold these indications with control pressures, gradually releasing them while applying rudder trim sufficient to relieve all rudder pressure. Apply aileron trim, if available, to relieve aileron pressure. With a full instrument panel, maintain a wings level attitude by reference to all available instruments while trimming the airplane. Turn and slip indicator, needle and ball, Unlike the turn coordinator that provides 3 indications, roll, turn, and trim, the turn and slip indicator provides 2, turn rate and trim. Although the turn and slip indicator needle provides an indication of turn only, it provides an indirect indication of aircraft attitude when used with roll indicators, such as a heading indicator or magnetic compass. As with the turn coordinator, after stabilizing from a roll, when the turn and slip indicator's needle is aligned with the alignment marks, the aircraft is in a standard turn of 3 degrees per second or 360 degrees in 2 minutes. The ball of the turn and bank indicator provides important trim in the same manner that the ball in the turn coordinator does. Figures 7 to 18 and 7 to 2019 provide a comparison of the two instruments. Power control power produces thrust which, with the appropriate angle of attack of the wing, overcomes the forces of gravity, drag, and inertia to determine airplane performance. Power control must be related to its effect on altitude and airspeed, since any change in power setting results in a change in the airspeed or the altitude of the airplane. At any given airspeed, the power setting determines whether the airplane is in level flight, in a climb, or in a descent. If the power is increased in straight and level flight and the airspeed held constant, the airplane climbs. If power is decreased while the airspeed is held constant, the airplane descends. On the other hand, if altitude is held constant, the power applied determines the airspeed. The relationship between altitude and airspeed determines the need for a change in pitch or power. If the airspeed is not the desired value, always check the altimeter before deciding that a power change is necessary. Think of altitude and airspeed as interchangeable. Altitude can be traded for airspeed by lowering the nose or convert airspeed to altitude by raising the nose. If altitude is higher than desired and airspeed is low, or vice versa, a change in pitch alone may return the airplane to the desired altitude and airspeed. Figure 720, if both airspeed and altitude are high or if both are low, then a change in both pitch and power is necessary in order to return to the desired airspeed and altitude. Figure 721, for changes in airspeed in straight and level flight, pitch, bank, and power must be coordinated in order to maintain constant altitude and heading. When power is changed to vary airspeed in straight and level flight, a single engine, propeller-driven airplane tends to change attitude around all axes of movement. Therefore, to maintain constant altitude and heading, apply various control pressures in proportion to the change in power. When power is added to increase airspeed, the pitch instruments indicate a climb unless forward elevator control pressure is applied as the airspeed changes. With an increase in power, the airplane tends to yaw and roll to the left unless counteracting aileron and rudder pressures are applied. Keeping ahead of these changes requires increasing cross-check speed, which varies with the type of airplane and its torque characteristics, the extent of power, and speed change involved. Power settings, power control and airspeed changes are much easier when approximate power settings necessary to maintain various airspeeds in straight and level flight are known in advance. However, to change airspeed by any appreciable amount, the common procedure is to underpower or overpower on initial power changes to accelerate the rate of airspeed change. For small speed changes, or in airplanes that decelerate or accelerate rapidly, overpowering or underpowering is not necessary. Consider the example of an airplane that requires 23 inches of mercury, Hg, of manifold pressure to maintain a normal cruising airspeed of 120 knots, and 18 Hg of manifold pressure to maintain an airspeed of 100 knots. The reduction in airspeed from 120 knots to 100 knots while maintaining straight and level flight is discussed below and illustrated in figures 7 to 22, 7 to 23 and 7 to 24. Instrument indications, prior to the power reduction, are shown in figure 722. The basic attitude is established and maintained on the attitude indicator. The specific pitch, bank, and power control requirements are detected on these primary instruments: altimeter, primary pitch heading indicator, primary bank airspeed indicator, primary power supporting pitch and bank instruments are shown in figure 723. Note that the supporting power instrument is the manifold pressure gauge, or tachometer if the propeller is fixed pitch. However, when a smooth power reduction to approximately 15 Hg under power is made, the manifold pressure gauge becomes the primary power instrument. Figure 723, with practice, power setting can be changed with only a brief glance at the power instrument, by sensing the movement of the throttle, the change in sound, and the changes in the feel of control pressures. As thrust decreases, increase the speed of the crosscheck and be ready to apply left rudder, back elevator, and aileron control pressure the instant the pitch and bank instruments show a deviation from altitude and heading. As proficiency is obtained, a pilot learns to cross-check, interpret, and control the changes with no deviation of heading and altitude. Assuming smooth air, an ideal control technique as airspeed decreases, a proportionate increase in airplane pitch attitude is required to maintain altitude. Similarly, effective torque control means counteracting yaw with rudder pressure. As the power is reduced, the altimeter is primary for pitch, the heading indicator is primary for bank, and the manifold pressure gauge is momentarily primary for power, at 15 Hg in this example. Control pressure should be trimmed off as the airplane decelerates. As the airspeed approaches the desired airspeed of 100 knots, the manifold pressure is adjusted to approximately 18 Hg and becomes the supporting power instrument. The AC again becomes primary for power. Figure 7.24, Airspeed changes in straight and level flight. Practice of airspeed changes in straight and level flight provides an excellent means of developing increased proficiency in all three basic instrument skills and brings out some common errors to be expected during training in straight and level flight. Having learned to control the airplane in a clean configuration, minimum drag conditions, increase proficiency in cross-check and control by practicing speed changes while extending or retracting the flaps and landing gear. While practicing, be sure to comply with the airspeed limitations specified in the PO/AFM for gear and flap operation. Sudden and exaggerated attitude changes may be necessary in order to maintain straight and level flight as the landing gear is extended and the flaps are lowered in some airplanes. The nose tends to pitch down with gear extension, and when flaps are lowered, lift increases momentarily, at partial flap settings, followed by a marked increase in drag as the flaps near maximum extension. Control technique varies according to the lift and drag characteristics of each airplane. Accordingly, knowledge of the power settings and trim changes associated with different combinations of airspeed, gear, and flap configurations reduces instrument cross-check and interpretation problems. For example, assume that in straight and level flight instruments indicate 120 knots with power at 23 Hg/2,300 revolutions per minute, RPM, gear and flaps up. After reduction in airspeed, with gear and flaps fully extended, straight and level flight at the same altitude requires 25 Hg manifold pressure/2,500 RPM. Maximum gear extension speed is 115 knots, maximum flap extension speed is 105 knots. Airspeed reduction to 95 knots, gear and flaps down, can be made in the following manner. 1. Maintain RPM at 2,500, since a high power setting is used in full drag configuration. 2. Reduce manifold pressure to 10 Hg. As the airspeed decreases, increase crosscheck speed. 3. Make trim adjustments for an increased angle of attack and decrease in torque. Pitch. 4. Lower the gear at 115 knots. The nose may tend to pitch down and the rate of deceleration increases. Increase pitch attitude to maintain constant altitude, and trim off some of the back elevator pressures. If full flaps are lowered at 105 knots, cross-check, interpretation, and control must be very rapid. A simpler technique is to stabilize attitude with gear down before lowering the flaps. 5. Since 18 Hg manifold pressure will hold level flight at 100 knots with the gear down, increase power smoothly to that setting until the AC shows approximately 105 knots. The attitude indicator now shows approximately 2.5 bar width nose high in straight and level flight. 6. Actuate the flap control and simultaneously increase power to the predetermined setting, 25 Hg, for the desired airspeed, and trim off the pressures necessary to hold constant altitude and heading. The attitude indicator now shows a bar width nose low in straight and level flight at 95 knots. Proficiency in straight and level flight is attained when a pilot can consistently maintain constant altitude and heading with smooth pitch, bank, power, and trim control during the pronounced changes in aircraft attitude. Trim technique. Proper trim technique is essential for smooth and precise aircraft control during all phases of flight. By relieving all control pressures, it is much easier to hold a given attitude constant and devote more attention to other flight deck duties. An aircraft is trimmed by applying control pressures to establish a desired attitude, then adjusting the trim so the aircraft maintains that attitude when the flight controls are released. Trim the aircraft for coordinated flight by centering the ball of the turn and slip indicator, by using rudder trim in the direction the ball is displaced from the center. Differential power control on multi-engine aircraft is an additional factor affecting coordinated flight. Use balanced power or thrust, when possible, to aid in maintaining coordinated flight. Changes in attitude, power, or configuration requires a trim adjustment in most cases. Using trim alone to establish a change in aircraft attitude invariably leads to erratic aircraft control. Smooth and precise attitude changes are best attained by a combination of control pressures and trim adjustments. Therefore, when used correctly, trim adjustment is an aid to smooth aircraft control. Common errors in straight and level flight pitch errors usually result from the following faults. 1. Improper adjustment of the attitude indicator's miniature aircraft to the wing's level attitude. Following the initial level off from a climb, check the attitude indicator and make any necessary adjustment in the miniature aircraft for level flight indication at normal cruise airspeed. 2. Insufficient cross-check and interpretation of pitch instruments. For example, the airspeed indication is low. The pilot, believing a nose-high attitude exists, applies forward pressure without noting that a low power setting is the cause of the airspeed discrepancy. Increase cross-check speed to include all relevant instrument indications before making a control input. 3. Uncaging the attitude indicator, if caging feature is present, when the airplane is not in level flight. The altimeter and heading indicator must be stabilized with airspeed indication at normal cruise before pulling out the caging knob to obtain correct indications in straight and level flight at normal cruise airspeed. 4. Failure to interpret the attitude indicator in terms of the existing airspeed. 5. Late pitch corrections. Pilots commonly like to leave well enough alone. When the altimeter indicates a 20-foot error, there is a reluctance to correct it, perhaps because of fear of over-controlling. If over-controlling is the anticipated error, practice small corrections and find the cause of over-controlling. If any deviation is tolerated, errors increase. 6. Chasing the vertical speed indications. This tendency can be corrected by proper cross-check of other pitch instruments, as well as by increasing overall understanding of instrument characteristics. 7. Using excessive pitch corrections for the altimeter evaluation. Rushing a pitch correction by making a large pitch change usually aggravates the existing error, saving neither time nor effort. 8. Failure to maintain established pitch corrections, a common error associated with cross-check and trim errors. For example, having established a pitch change to correct an altitude error, there is a tendency to slow down the cross-check, waiting for the airplane to stabilize in the new pitch attitude. To maintain the attitude, continue to cross-check and trim off the pressures. 9. Fixations during cross-check. After initiating a heading correction, for example, there is a tendency to become preoccupied with bank control and miss errors in pitch attitude. Likewise, during an airspeed change, unnecessary gazing at the power instrument is common. A small error in power setting is of less consequence than large altitude and heading errors. The airplane will not decelerate any faster by staring at the manifold pressure gauge. Heading errors usually result from the following faults. 1. Failure to cross-check the heading indicator, especially during changes in power or pitch attitude. 2. Misinterpretation of changes in heading, with resulting corrections in the wrong direction. 3. Failure to note and remember a preselected heading. 4. Failure to observe the rate of heading change and its relation to bank attitude. 5. Over-controlling in response to heading changes, especially during changes in power settings. 6. Anticipating heading changes with premature application of rudder control. 7. Failure to correct small heading deviations. Unless zero error in heading is the goal, a pilot will tolerate larger and larger deviations. Correction of a 1-degree error takes a lot less time and concentration than correction of a 20 degrees error. 8. Correcting with improper bank attitude. If correcting a 10 degrees heading error with 20 degrees of bank, the airplane rolls past the desired heading before the bank is established, requiring another correction in the opposite direction. Do not multiply existing errors with errors in corrective technique. 9. Failure to note the cause of a previous heading error and thus repeating the same error. For example, the airplane is out of trim, with a left wing low tendency. Repeated corrections for a slight left turn are made, yet trim is ignored. 10. Failure to set the heading indicator properly or failure to uncage it. Power errors usually result from the following faults. 1. Failure to know the power settings and pitch attitudes appropriate to various airspeeds and airplane configurations. 2. Abrupt use of throttle. 3. Failure to lead the airspeed when making power changes. For example, during airspeed reduction in level flight, especially with gear and flaps extended, Adjust the throttle to maintain the slower speed before the airspeed actually reaches the desired speed. Otherwise, the airplane decelerates to a speed lower than that desired, resulting in additional power adjustments. The amount of lead depends upon how fast the airplane responds to power changes. 4. Fixation on airspeed or manifold pressure instruments during airspeed changes, resulting in erratic control of both airspeed and power. Trim errors usually result from the following faults. 1. Improper adjustment of seat or rudder pedals for comfortable position of legs and feet. Tension in the ankles makes it difficult to relax rudder pressures. 2. Confusion about the operation of trim devices that differ among various airplane types. Some trim wheels are aligned appropriately with the airplane's axis, others are not. Some rotate in a direction contrary to what is expected. 3. Faulty sequence in trim technique. Trim should be used not as a substitute for control with the wheel, stick, and rudders, but to relieve pressures already held to stabilize attitude. As proficiency is gained, little conscious effort is required to trim off the pressures as they occur. 4. Excessive trim control. This induces control pressures that must be held until the airplane is trimmed properly. Use trim frequently and in small amounts. 5. Failure to understand the cause of trim changes. Lack of understanding the basic aerodynamics related to basic instrument skills causes a pilot to continually lag behind the airplane. Straight climbs and descents climbs for a given power setting and load condition, there is only one attitude that gives the most efficient rate of climb. The airspeed and climb power setting that determines this climb attitude are given in the performance data found in the PO/AFM. Details of the technique for entering a climb vary according to airspeed on entry and the type of climb, constant airspeed or constant rate desired. Heading and trim control are maintained as discussed in straight and level flight. Entry: to enter a constant airspeed climb from cruising airspeed, raise the miniature aircraft to the approximate nose-high indication for the predetermined climb speed. The attitude varies according to the type of airplane. Apply light back elevator pressure to initiate and maintain the climb attitude. The pressures vary as the airplane decelerates. Power may be advanced to the climb power setting simultaneously with the pitch change or after the pitch change is established and the airspeed approaches climb speed. If the transition from level flight to climb is smooth, the VSI shows an immediate trend upward, continues to move slowly, and then stops at a rate appropriate to the stabilized airspeed and attitude. Primary and supporting instruments for the climb entry are shown in Figure 725. Once the airplane stabilizes at a constant airspeed and attitude, the AC is primary for pitch and the heading indicator remains primary for bank. Figure 726, monitor the tachometer or manifold pressure gauge as the primary power instrument to ensure the proper climb power setting is being maintained. If the climb attitude is correct for the power setting selected, the airspeed will stabilize at the desired speed. If the airspeed is low or high, make an appropriately small pitch correction. To enter a constant airspeed climb, first complete the airspeed reduction from cruise airspeed to climb speed in straight and level flight. The climb entry is then identical to entry from cruising airspeed, except that power must be increased simultaneously to the climb setting as the pitch attitude is increased. Climb entries on partial panel are more easily and accurately controlled if entering the maneuver from climbing speed. The technique for entering a constant rate climb is very similar to that used for entry to a constant airspeed climb from climb airspeed. As the power is increased to the approximate setting for the desired rate, simultaneously raise the miniature aircraft to the climbing attitude for the desired airspeed and rate of climb. As the power is increased, the AC is primary for pitch control until the vertical speed approaches the desired value. As the vertical speed needle stabilizes, it becomes primary for pitch control and the AC becomes primary for power control. Figure 727. Pitch and power corrections must be promptly and closely coordinated. For example, if the vertical speed is correct, but the airspeed is low, add power. As the power is increased, the miniature aircraft must be lowered slightly to maintain constant vertical speed. If the vertical speed is high and the airspeed is low, lower the miniature aircraft slightly and note the increase in airspeed to determine whether or not a power change is also necessary. Figure 728, familiarity with the approximate power settings helps to keep pitch and power corrections at a minimum. Leveling off: to level off from a climb and maintain an altitude, it is necessary to start the level off before reaching the desired altitude. The amount of lead varies with rate of climb and pilot technique. If the airplane is climbing at 1000 fpm, it continues to climb at a decreasing rate throughout the transition to level flight. An effective practice is to lead the altitude by 10% of the vertical speed shown, 500 fpm/50 foot lead, 1000 fpm/100 foot lead. To level off at cruising airspeed, apply smooth, steady forward elevator pressure toward level flight attitude for the speed desired. As the attitude indicator shows the pitch change, the vertical speed needle moves slowly toward zero, the altimeter needle moves more slowly, and the airspeed shows acceleration. Figure 729, when the altimeter, attitude indicator, and VSI show level flight, constant changes in pitch and torque control have to be made as the airspeed increases. As the airspeed approaches cruising speed, reduce power to the cruise setting. The amount of lead depends upon the rate of acceleration of the airplane. To level off at climbing airspeed, lower the nose to the pitch attitude appropriate to that airspeed and level flight. Power is simultaneously reduced to the setting for that airspeed as the pitch attitude is lowered. If power reduction is at a rate proportionate to the pitch change, airspeed will remain constant. Descents at descent can be made at a variety of airspeeds and attitudes by reducing power, adding drag, and lowering the nose to a predetermined attitude. The airspeed eventually stabilizes at a constant value. Meanwhile, the only flight instrument providing a positive attitude reference is the attitude indicator. Without the attitude indicator, such as during a partial panel descent, the AC, altimeter, and VSI show varying rates of change until the airplane decelerates to a constant airspeed at a constant attitude. During the transition, changes in control pressure and trim, as well as crosscheck and interpretation, must be accurate to maintain positive control. Entry: the following method for entering descents is effective with or without an attitude indicator. First, reduce airspeed to a selected descent airspeed while maintaining straight and level flight, then make a further reduction in power, to a predetermined setting. As the power is adjusted, simultaneously lower the nose to maintain constant airspeed, and trim off control pressures. During a constant airspeed descent, any deviation from the desired airspeed calls for a pitch adjustment. For a constant rate descent, the entry is the same, but the VSI is primary for pitch control, after it stabilizes near the desired rate, and the AC is primary for power control. Pitch and power must be closely coordinated when corrections are made, as they are in climbs. Figure 730, leveling off: the level off from a descent must be started before reaching the desired altitude. The amount of lead depends upon the rate of descent and control technique. With too little lead, the airplane tends to overshoot the selected altitude unless technique is rapid. Assuming a 500 fpm rate of descent, lead the altitude by 100 to 150 feet for a level off at an airspeed higher than descending speed. At the lead point, add power to the appropriate level flight cruise setting. Figure 731, since the nose tends to rise as the airspeed increases, hold forward elevator pressure to maintain the vertical speed at the descending rate until approximately 50 feet above the altitude, and then smoothly adjust the pitch attitude to the level flight attitude for the airspeed selected. To level off from a descent at descent airspeed, lead the desired altitude by approximately 50 feet, simultaneously adjusting the pitch attitude to level flight and adding power to a setting that holds the airspeed constant. Figure 732, trim off the control pressures and continue with the normal straight and level flight crosscheck. Common errors in straight climbs and descents: common errors result from the following faults. 1. Over-controlling pitch on climb entry. Until the pitch attitudes related to specific power settings used in climbs and descents are known, larger than necessary pitch adjustments are made. One of the most difficult habits to acquire during instrument training is to restrain the impulse to disturb a flight attitude until the result is known. Overcome the inclination to make a large control movement for a pitch change, and learn to apply small control pressures smoothly, cross-checking rapidly for the results of the change, and continuing with the pressures as instruments show the desired results. Small pitch changes can be easily controlled, stopped, and corrected. Large changes are more difficult to control. Two. Failure to vary the rate of crosscheck during speed, power, or attitude changes or climb or descent entries. 3. Failure to maintain a new pitch attitude. For example, raising the nose to the correct climb attitude, and as the airspeed decreases, either over-control and further increase the pitch attitude or allow the nose to lower. As control pressures change with airspeed changes, crosscheck must be increased and pressures readjusted. 4. Failure to trim off pressures. Unless the airplane is trimmed, there is difficulty in determining whether control pressure changes are induced by aerodynamic changes or by the pilot's own movements. 5. Failure to learn and use proper power settings. 6. Failure to cross-check both airspeed and vertical speed before making pitch or power adjustments. 7. Improper pitch and power coordination on slow speed level-offs due to slow cross-check of airspeed and altimeter indications. 8. Failure to cross-check the VSI against the other pitch control instruments, resulting in chasing the vertical speed. 9. Failure to note the rate of climb or descent to determine the lead for level-offs, resulting in overshooting or undershooting the desired altitude. 10. Ballooning, allowing the nose to pitch up, on level-offs from descents, resulting from failure to maintain descending attitude with forward elevator pressure as power is increased to the level flight cruise setting. 11. Failure to recognize the approaching straight and level flight indications as level-off is completed. Maintain an accelerated cross-check until positively established in straight and level flight. Turns standard rate turns. A standard rate turn is one in which the pilot will do a complete 360 degrees circle in 2 minutes or 3 degrees per second. A standard rate turn, although always 3 degrees per second, requires higher angles of bank as airspeed increases. To enter a standard rate level turn, apply coordinated aileron and rudder pressures in the desired direction of turn. Pilots commonly roll into turns at a much too rapid rate. During initial training in turns, base control pressures on the rate of cross-check and interpretation. Maneuvering an airplane faster than the capability to keep up with the changes in instrument indications only creates the need to make corrections. A rule of thumb to determine the approximate angle of bank required for a standard rate turn is to use 15% of the true airspeed. A simple way to determine this amount is to divide the airspeed by 10 and add 1/2 the result. For example, at 100 knots, approximately 15 degrees of bank is required. 100 divided by 10 equals 10 plus 5 equals 15. At 120 knots, approximately 18 degrees of bank is needed for a standard rate turn. On the roll-in, use the attitude indicator to establish the approximate angle of bank, and then check the turn coordinator's miniature aircraft for a standard rate turn indication or the aircraft's turn and bank indicator. Maintain the bank for this rate of turn, using the turn coordinator's miniature aircraft as the primary bank reference and the attitude indicator as the supporting bank instrument. Figure 7 to 33, note the exact angle of bank shown on the banking scale of the attitude indicator when the turn coordinator indicates a standard rate turn. During the roll-in, check the altimeter, VSI, and attitude indicator for the necessary pitch adjustments as the vertical lift component decreases with an increase in bank. If constant airspeed is to be maintained, the AC becomes primary for power, and the throttle must be adjusted as drag increases. As the bank is established, trim off the pressures applied during pitch and power changes. To recover to straight and level flight, apply coordinated aileron and rudder pressures opposite to the direction of the turn. Strive for the same rate of rollout used to roll into the turn. Fewer problems are encountered in estimating the lead necessary for rollout on exact headings, especially on partial panel maneuvers. Upon initiation of the turn recovery, the attitude indicator becomes the primary bank instrument. When the airplane is approximately level, the heading indicator is the primary bank instrument as in straight and level flight. Pitch, power, and trim adjustments are made as changes in vertical lift component and airspeed occur. The ball should be checked throughout the turn, especially if control pressures are held rather than trimmed off. Some airplanes are very stable during turns, requiring only slight trim adjustments that permit hands-off flight while the airplane remains in the established attitude. Other airplanes require constant, rapid cross-check and control during turns to correct overbanking tendencies. Due to the interrelationship of pitch, bank, and airspeed deviations during turns, cross-check must be fast in order to prevent an accumulation of errors. Turns to predetermined headings. As long as an airplane is in a coordinated bank, it continues to turn. Thus, the rollout to a desired heading must be started before the heading is reached. The amount of lead varies with the relationship between the rate of turn, angle of bank, and rate of recovery. For small heading changes, use a bank angle that does not exceed the number of degrees to be turned. Lead the desired heading by 1/2 the number of degrees of bank used. For example, if a 10 degrees bank is used during a change in heading, start the rollout 5 degrees before reaching the desired heading. For larger changes in heading, the amount of lead varies since the angle of bank for a standard rate turn varies with the true airspeed. Practice with a lead of 1/2 the angle of bank until the precise lead a given technique requires is determined. If rates of roll-in and roll-out are consistent, the precise amount of lead suitable to a particular rollout technique can be determined. Time turns. A time turn is a turn in which the clock and the turn coordinator are used to change heading by a specific number of degrees in a given time. For example, in a standard rate turn, 3 degrees per second, an airplane turns 45 degrees in 15 seconds. In a half standard rate turn, the airplane turns 45 degrees in 30 seconds. Prior to performing time turns, the turn coordinator should be calibrated to determine the accuracy of its indications. Figure 734, establish a standard rate turn as indicated by the turn coordinator, and as the sweep second hand of the clock passes a cardinal point, 12, 3, 6, 9, check the heading on the heading indicator. While holding the indicated rate of turn constant, note the indicated heading changes at 10 seconds intervals. If the airplane turns more than or less than 30 degrees in that interval, a respectively larger or smaller deflection of the miniature aircraft of the turn coordinator is necessary to produce a standard rate turn. After calibrating the turn coordinator during turns in each direction, note the corrected deflections, if any, and apply them during all time turns. The same cross-check and control technique is used in making a time turn that is used to execute turns to predetermined headings, except the clock is substituted for the heading indicator. The miniature aircraft of the turn coordinator is primary for bank control, the altimeter is primary for pitch control, and the AC is primary for power control. Start the roll-in when the clock's second hand passes a cardinal point, hold the turn at the calibrated standard rate indication, or half standard rate for small heading changes, and begin the rollout when the computed number of seconds has elapsed. If the rates of roll-in and roll-out are the same, the time taken during entry and recovery does not need to be considered in the time computation. Practice time turns with a full instrument panel and check the heading indicator for the accuracy of turns. If the turns are executed without the gyro heading indicator, use the magnetic compass at the completion of the turn to check turn accuracy, taking compass deviation errors into consideration. Compass turns in most small airplanes, the magnetic compass is the only direction indicating instrument independent of other airplane instruments and power sources. Because of its operating characteristics, called compass errors, pilots are prone to use it only as a reference for setting the heading indicator, but knowledge of magnetic compass characteristics permits full use of the instrument to turn the airplane to correct and maintain headings. Remember the following points when making turns to magnetic compass headings or when using the magnetic compass as a reference for setting the heading indicator. 1. If on a north heading and a turn is started to the east or west, the compass indication lags or indicates a turn in the opposite direction. 2. If on a south heading and a turn is started toward the east or west, the compass indication precedes the turn, indicating a greater amount of turn than is actually occurring. 3. When on an east or west heading, the compass indicates correctly when starting a turn in either direction. 4. If on an east or west heading, acceleration results in a north turn indication, deceleration results in a south turn indication. 5. When maintaining a north or south heading, no error results from diving, climbing, or changing airspeed. With an angle of bank between 15 degrees and 18 degrees, the amount of lead or lag to be used when turning to northerly or southerly headings varies with, and is approximately equal to, the latitude of the locality over which the turn is being made. When turning to a heading of north, the lead for rollout must include the number of degrees of change of latitude, plus the lead normally used in recovery from turns. During a turn to a south heading, maintain the turn until the compass passes south the number of degrees of latitude, minus normal rollout lead. Figure 735, for example, when turning from an easterly direction to north, where the latitude is 30 degrees, start the rollout when the compass reads 37 degrees, 30 degrees plus 1/2 the 15 degrees angle of bank, or whatever amount is appropriate for the rate of rollout. When turning from an easterly direction to south, start the rollout when the magnetic compass reads 203 degrees, 180 degrees plus 30 degrees minus 1/2 the angle of bank. When making similar turns from a westerly direction, the appropriate points at which to begin the rollout would be 323 degrees for a turn to north and 157 degrees for a turn to south. When turning to a heading of east or west from a northerly direction, start the rollout approximately 10 degrees to 12 degrees before the east or west indication is reached. When turning to an east or west heading from a southerly direction, start the rollout approximately 5 degrees before the east or west indication is reached. When turning to other headings, the lead or lag must be interpolated. Abrupt changes in attitude or airspeed and the resulting erratic movements of the compass card make accurate interpretations of the instrument very difficult. Proficiency in compass turns. Figure 535 depends on knowledge of compass characteristics, smooth control technique, and accurate bank and pitch control. Steep turns. For purposes of instrument flight training in conventional airplanes, any turn greater than a standard rate is considered steep. Figure 7 to 36, the exact angle of bank at which a normal turn becomes steep is unimportant. What is important is learning to control the airplane with bank attitudes in excess of those normally used on instruments. Practicing steep turns will not only increase proficiency in the basic instrument flying skills, but also enable smooth, quick, and confident reactions to unexpected abnormal flight attitudes under instrument flight conditions. Pronounced changes occur in the effects of aerodynamic forces on aircraft control at progressively greater bank attitudes. Skill in crosscheck, interpretation, and control is increasingly necessary in proportion to the amount of these changes, though the techniques for entering, maintaining, and recovering from the turn are the same in principle for steep turns as for shallower turns. Enter a steep turn in the same way as a shallower turn, but prepare to crosscheck rapidly as the turn steepens. Because of the greatly reduced vertical lift component, pitch control is usually the most difficult aspect of this maneuver. Unless immediately noted and corrected with a pitch increase, the loss of vertical lift results in rapid movement of the altimeter, vertical speed, and airspeed needles. The faster the rate of bank change, the more suddenly the lift changes occur. If a crosscheck is fast enough to note the immediate need for pitch changes, smooth, steady back elevator pressure will maintain constant altitude. However, overbanking to excessively steep angles without adjusting pitch as the bank changes occur requires increasingly stronger elevator pressure. The loss of vertical lift and increase in wing loading finally reach a point at which further application of back elevator pressure tightens the turn without raising the nose. How does a pilot recognize overbanking and low pitch attitude? What should a pilot do to correct them? If a rapid downward movement of the altimeter needle or vertical speed needle, together with an increase in airspeed, is observed despite application of back elevator pressure, the airplane is in a diving spiral. Figure 737, immediately shallow the bank with smooth and coordinated aileron and rudder pressures, hold or slightly relax elevator pressure, and increase the cross-check of the attitude indicator, altimeter, and VSI. Reduce power if the airspeed increase is rapid. When the vertical speed trends upward, the altimeter needle moves slower as the vertical lift increases. When the elevator is effective in raising the nose, hold the bank attitude shown on the attitude indicator and adjust elevator control pressures smoothly for the nose high attitude appropriate to the bank maintained. If pitch control is consistently late on entries to steep turns, roll out immediately to straight and level flight and analyze possible errors. Practice shallower turns initially and learn the attitude changes and control responses required. Then increase the banks as a quicker and more accurate cross-check and control techniques are developed. The power necessary to maintain constant airspeed increases as the bank and drag increase. With practice, the power settings appropriate to specific bank attitudes are learned, and adjustments can be made without undue attention to airspeed and power instruments. During training in steep turns, as in any other maneuver, attend to the most important tasks first. Keep the pitch attitude relatively constant, and more time can be devoted to crosscheck and instrument interpretation. During recovery from steep turns to straight and level flight, elevator and power control must be coordinated with bank control in proportion to the changes in aerodynamic forces. Back elevator pressures must be released and power decreased. The common errors associated with steep turns are the same as those discussed later in this section. Remember, errors are more exaggerated, more difficult to correct, and more difficult to analyze unless rates of entry and recovery are consistent with the level of proficiency in the three basic instrument flying skills. Climbing and descending turns. To execute climbing and descending turns, combine the technique used in straight climbs and descents with the various turn techniques. The aerodynamic factors affecting lift and power control must be considered in determining power settings, and the rate of crosscheck and interpretation must be increased to enable control of bank as well as pitch changes. Change of airspeed during turns. Changing airspeed during turns is an effective maneuver for increasing proficiency in all three basic instrument skills. Since the maneuver involves simultaneous changes in all components of control, proper execution requires rapid crosscheck and interpretation as well as smooth control. Proficiency in the maneuver also contributes to confidence in the instruments during attitude and power changes involved in more complex maneuvers. Pitch and power control techniques are the same as those used during changes in airspeed in straight and level flight. The angle of bank necessary for a given rate of turn is proportional to the true airspeed. Since the turns are executed at a standard rate, the angle of bank must be varied in direct proportion to the airspeed change in order to maintain a constant rate of turn. During a reduction of airspeed, decrease the angle of bank and increase the pitch attitude to maintain altitude in a standard rate turn. The altimeter and turn coordinator indication should remain constant throughout the turn. The altimeter is primary for pitch control and the miniature aircraft of the turn coordinator is primary for bank control. The manifold pressure gauge, or tachometer, is primary for power control while the airspeed is changing. As the airspeed approaches the new indication, the AC becomes primary for power control. Two methods of changing airspeed in turns may be used. In the first method, airspeed is changed after the turn is established. Figure 738, in the second method, the airspeed change is initiated simultaneously with the turn entry. The first method is easier, but regardless of the method used, the rate of cross-check must be increased as power is reduced. As the airplane decelerates, check the altimeter and VSI for necessary pitch changes and the bank instruments for required bank changes. If the miniature aircraft of the turn coordinator indicates a deviation from the desired deflection, adjust the bank. Adjust pitch attitude to maintain altitude. When approaching the desired airspeed, pitch attitude becomes primary for power control and the manifold pressure gauge, or tachometer, is adjusted to maintain the desired airspeed. Trim is important throughout the maneuver to relieve control pressures. Until control technique is very smooth, frequent cross-check of the attitude indicator is essential to prevent over-controlling and to provide approximate bank angles appropriate to the changing airspeeds. Common errors in turns. Pitch errors result from the following faults. 1. Preoccupation with bank control during turn entry and recovery. If 5 seconds are required to roll into a turn, check the pitch instruments as bank pressures are initiated. If bank control pressure and rate of bank change are consistent, a sense of the time required for an attitude change is developed. During the interval, check pitch, power, and trim, as well as bank, controlling the total attitude instead of one factor at a time. 2. Failure to understand or remember the need for changing the pitch attitude as the vertical lift component changes, resulting in consistent loss of altitude during entries. 3. Changing the pitch attitude before it is necessary. This fault is very likely if a cross-check is slow and rate of entry too rapid. The error occurs during the turn entry due to a mechanical and premature application of backed elevator control pressure. 4. Over-controlling the pitch changes. This fault commonly occurs with the previous error. 5. Failure to properly adjust the pitch attitude as the vertical lift component increases during the rollout, resulting in consistent gain in altitude on recovery to headings. 6. Failure to trim during turn entry and following turn recovery, if turn is prolonged. 7. Failure to maintain straight and level cross-check after rollout. This error commonly follows a perfectly executed turn. 8. Erratic rates of bank change on entry and recovery, resulting from failure to cross-check the pitch instruments with a consistent technique appropriate to the changes in lift. Bank and heading errors result from the following faults. 1. Over-controlling, resulting in overbanking upon turn entry, overshooting and undershooting headings, as well as aggravated pitch, airspeed, and trim errors. 2. Fixation on a single bank instrument. On a 90 degrees change of heading, for example, leave the heading indicator out of the crosscheck for approximately 20 seconds after establishing a standard rate turn, since at 3 degrees per second the turn will not approach the lead point until that time has elapsed. Make the crosscheck selective, checking only what needs to be checked at the appropriate time. 3. Failure to check for precession of the horizon bar following recovery from a turn. If the heading indicator shows a change in heading when the attitude indicator shows level flight, the airplane is turning. If the ball is centered, the attitude gyro has precessed. If the ball is not centered, the airplane may be in a slipping or skidding turn. Center the ball with rudder pressure, check the attitude indicator and heading indicator, stop the heading change if it continues, and retrim. 4. Failure to use the proper degree of bank for the amount of heading change desired. Rolling into a 20 degrees bank for a heading change of 10 degrees will normally overshoot the heading. Use the bank attitude appropriate to the amount of heading change desired. 5. Failure to remember the heading to which the aircraft is being turned. This fault is likely when rushing the maneuver. 6. Turning in the wrong direction, due to misreading or misinterpreting the heading indicator, or to confusion regarding the location of points on the compass. Turn in the shortest direction to reach a given heading, unless there is a specific reason to turn the long way around. Study the compass rose and visualize at least the positions of the 8 major points around the azimuth. A number of methods can be used to make quick computations for heading changes. For example, to turn from a heading of 305 degrees to a heading of 110 degrees, would a pilot turn right or left for the shortest way around? Subtracting 200 from 305 and adding 20 gives 125 degrees as the reciprocal of 305 degrees, therefore, execute the turn to the right. Likewise, to figure the reciprocal of a heading less than 180 degrees, add 200 and subtract 20. Computations are done more quickly using multiples of 100s and 10s than by adding or subtracting 180 degrees from the actual heading, therefore, the method suggested above may save time and confusion. 7. Failure to check the ball of the turn coordinator when interpreting the instrument for bank information. If the roll rate is reduced to 0, the miniature aircraft of the turn coordinator indicates only direction and rate of turn. Unless the ball is centered, do not assume the turn is resulting from a banked attitude. Power and airspeed errors result from the following faults. 1. Failure to cross-check the AC as pitch changes are made. 2. Erratic use of power control. This may be due to improper throttle friction control, inaccurate throttle settings, chasing the airspeed readings, abrupt or over-controlled pitch and bank changes, or failure to recheck the airspeed to note the effect of a power adjustment. 3. Poor coordination of throttle control with pitch and bank changes associated with slow cross-check or failure to understand the aerodynamic factors related to turns. Trim errors result from the following faults. 1. Failure to recognize the need for a trim change due to slow cross-check and interpretation. For example, a turn entry at a rate too rapid for a cross-check leads to confusion in cross-check and interpretation with resulting tension on the controls. 2. Failure to understand the relationship between trim and attitude/power changes. 3. Chasing the vertical speed needle. Over-controlling leads to tension and prevents sensing the pressures to be trimmed off. 4. Failure to trim following power changes. Errors during compass turns. In addition to the faults discussed above, the following errors connected with compass turns should be noted. 1. Faulty understanding or computation of lead and lag. 2. Fixation on the compass during the rollout. Until the airplane is in straight and level unaccelerated flight, it is unnecessary to read the indicated heading. Accordingly, after the rollout, cross-check for straight and level flight before checking the accuracy of the turn. Approach to stall. Practicing approach to stall recoveries in various airplane configurations should build confidence in a pilot's ability to control the airplane in unexpected situations. Approach to stall should be practiced from straight flight and from shallow banks. The objective is to practice recognition and recovery from the approach to a stall. Prior to stall recovery practice, select a safe altitude above the terrain, an area free of conflicting air traffic, appropriate weather, and the availability of radar traffic advisory service. Approaches to stalls are accomplished in the following configurations. 1. Takeoff configuration should begin from level flight near liftoff speed. Power should be applied while simultaneously increasing the angle of attack to induce an indication of a stall. 2. Clean configuration should begin from a reduced airspeed, such as pattern airspeed, in level flight. Power should be applied while simultaneously increasing the angle of attack to induce an indication of a stall. 3. Approach or landing configuration should be initiated at the appropriate approach or landing airspeed. The angle of attack should be smoothly increased to induce an indication of a stall. Recovery should be prompt in response to a stall warning device or an aerodynamic indication by smoothly reducing the angle of attack and applying maximum power or as recommended by the PO/AFM. The recovery should be completed without an excessive loss of altitude and on a predetermined heading, altitude, and airspeed. Unusual attitudes and recoveries. An unusual attitude is an airplane attitude not normally required for instrument flight. Unusual attitudes may result from a number of conditions, such as turbulence, disorientation, instrument failure, confusion, preoccupation with flight deck duties, carelessness in cross-checking, errors in instrument interpretation, or lack of proficiency in aircraft control. Since unusual attitudes are not intentional maneuvers during instrument flight, except in training, they are often unexpected, and the reaction of an inexperienced or inadequately trained pilot to an unexpected abnormal flight attitude is usually instinctive rather than intelligent and deliberate. This individual reacts with abrupt muscular effort, which is purposeless and even hazardous in turbulent conditions, at excessive speeds, or at low altitudes. However, with practice, the techniques for rapid and safe recovery from unusual attitudes can be mastered. When an unusual attitude is noted during the crosscheck, the immediate problem is not how the airplane got there, but what it is doing and how to get it back to straight and level flight as quickly as possible. Recognizing unusual attitudes as a general rule, anytime an instrument rate of movement or indication other than those associated with the basic instrument flight maneuvers is noted, assume an unusual attitude and increase the speed of crosscheck to confirm the attitude, instrument error, or instrument malfunction. Nose-high attitudes are shown by the rate and direction of movement of the altimeter needle, vertical speed needle, and airspeed needle, as well as the immediately recognizable indication of the attitude indicator, except in extreme attitudes. Figure 7 to 39, nose-low attitudes are shown by the same instruments, but in the opposite direction. Figure 740, recovery from unusual attitudes. In moderate unusual attitudes, the pilot can normally reorient by establishing a level flight indication on the attitude indicator. However, the pilot should not depend on this instrument if the attitude indicator is the spillable type, because its upset limits may have been exceeded or it may have become inoperative due to mechanical malfunction. If it is the non-spillable type instrument and is operating properly, errors up to 5 degrees of pitch and bank may result, and its indications are very difficult to interpret in extreme attitudes. As soon as the unusual attitude is detected, the recommended recovery procedures stated in the PO/AFM should be initiated. If there are no recommended procedures stated in the PO/AFM, the recovery should be initiated by reference to the AC, altimeter, VSI, and turn coordinator. Nose-high attitudes. If the airspeed is decreasing, or below the desired airspeed, increase power, as necessary in proportion to the observed deceleration, apply forward elevator pressure to lower the nose and prevent a stall, and correct the bank by applying coordinated aileron and rudder pressure to level the miniature aircraft and center the ball of the turn coordinator. The corrective control applications are made almost simultaneously, but in the sequence given above. A level pitch attitude is indicated by the reversal and stabilization. Figure 740. Unusual attitude, nose low. Of the AC and altimeter needles. Straight coordinated flight is indicated by the level miniature aircraft and centered ball of the turn coordinator. Nose low attitudes. If the airspeed is increasing, or is above the desired airspeed, reduce power to prevent excessive airspeed and loss of altitude. Correct the bank attitude with coordinated aileron and rudder pressure to straight flight by referring to the turn coordinator. Raise the nose to level flight attitude by applying smooth back elevator pressure. All components of control should be changed simultaneously for a smooth, proficient recovery. However, during initial training, a positive, confident recovery should be made by the numbers, in the sequence given above. A very important point to remember is that the instinctive reaction to a nose-down attitude is to pull back on the elevator control. After initial control has been applied, continue with a fast cross-check for possible over-controlling, since the necessary initial control pressures may be large. As the rate of movement of altimeter and AC needles decreases, the attitude is approaching level flight. When the needles stop in reverse direction, the aircraft is passing through level flight. As the indications of the AC, altimeter, and turn coordinator stabilize, incorporate the attitude indicator into the crosscheck. The attitude indicator and turn coordinator should be checked to determine bank attitude, and then corrective aileron and rudder pressures should be applied. The ball should be centered. If it is not, skidding and slipping sensations can easily aggravate disorientation and retard recovery. If entering the unusual attitude from an assigned altitude, either by an instructor or by air traffic control, ATC, if operating under instrument flight rules, IFR, return to the original altitude after stabilizing in straight and level flight. Common errors in unusual attitudes. Common errors associated with unusual attitudes include the following faults. 1. Failure to keep the airplane properly trimmed. A flight deck interruption when holding pressures can easily lead to inadvertent entry into unusual attitudes. 2. Disorganized flight deck. Hunting for charts, logs, computers, etc., can seriously distract attention from the instruments. 3. Slow crosscheck and fixations. The impulse is to stop and stare when noting an instrument discrepancy unless a pilot has trained enough to develop the skill required for immediate recognition. 4. Attempting to recover by sensory sensations other than sight. The discussion of disorientation in Chapter 3, Human Factors, indicates the importance of trusting the instruments. 5. Failure to practice basic instrument skills. All of the errors noted in connection with basic instrument skills are aggravated during unusual attitude recoveries until the elementary skills have been mastered. Instrument takeoff competency. Instrument takeoffs will provide the proficiency and confidence necessary for use of flight instruments during departures under conditions of low visibility, rain, low ceilings, or disorientation at night. A sudden rapid transition from visual to instrument flight can result in serious disorientation and control problems. Instrument takeoff techniques vary with different types of airplanes, but the method described below is applicable whether the airplane is single or multi-engine, tricycle gear or conventional gear. Align the airplane with the centerline of the runway with the nose wheel or tail wheel straight. Lock the tail wheel, if so equipped, and hold the brakes firmly to avoid creeping while preparing for takeoff. Set the heading indicator with the nose index on the 5-degree mark nearest the published runway heading to allow instant detection of slight changes in heading during the takeoff. Make certain that the instrument is uncaged, if it has a caging feature, by rotating the knob after uncaging and checking for constant heading indication. If using an electric heading indicator with a rotatable needle, rotate the needle so that it points to the nose position, under the top index. Advance the throttle to an RPM that will provide partial rudder control. Release the brakes, advancing the power smoothly to takeoff setting. During the takeoff roll, hold the heading constant on the heading indicator by using the rudder. In multi-engine, propeller-driven airplanes, also use differential throttle to maintain direction. The use of brakes should be avoided, except as a last resort, as it usually results in over-controlling and extending the takeoff roll. Once the brakes are released, any deviation in heading must be corrected instantly. As the airplane accelerates, cross-check both heading indicator and AC rapidly. The attitude indicator may precess to a slight nose-up attitude. As flying speed is approached, approximately 15 to 25 knots below takeoff speed, smoothly apply elevator control for the desired takeoff attitude on the attitude indicator. This is approximately a 2-bar width climb indication for most small airplanes. Continue with a rapid cross-check of heading indicator and attitude indicator as the airplane leaves the ground. Do not pull it off, let it fly off while holding the selected attitude constant. Maintain pitch and bank control by referencing the attitude indicator, and make coordinated corrections in heading when indicated on the heading indicator. Cross-check the altimeter and VSI for a positive rate of climb, steady clockwise rotation of the altimeter needle, and the VSI showing a stable rate of climb appropriate to the airplane. When the altimeter shows a safe altitude, approximately 100 feet, raise the landing gear and flaps, maintaining attitude by referencing the attitude indicator. Because of control pressure changes during gear and flap operation, over-controlling is likely unless the pilot notes pitch indications accurately and quickly. Trim off control pressures necessary to hold the stable climb attitude. Check the altimeter, VSI, and airspeed for a smooth acceleration to the predetermined climb speed, altimeter and airspeed increasing, vertical speed stable. At climb speed, reduce power to climb setting, unless full power is recommended for climb by the post/AFM and trim. Throughout the instrument takeoff, cross-check and interpretation must be rapid and control positive and smooth. During liftoff, gear and flap retraction, power reduction, and the changing control reactions demand rapid cross-check, adjustment of control pressures, and accurate trim changes. Common errors in instrument takeoffs. Common errors during the instrument takeoff include the following. 1. Failure to perform an adequate flight deck check before the takeoff. Pilots have attempted instrument takeoffs with inoperative airspeed indicators, pitot tube obstructed, gyros caged, controls locked, and numerous other oversights due to haste or carelessness. 2. Improper alignment on the runway. This may result from improper brake application, allowing the airplane to creep after alignment, or from alignment with the nose wheel or tail wheel cocked. In any case, the result is a built-in directional control problem as the takeoff starts. 3. Improper application of power. Abrupt application of power complicates directional control. Add power with a smooth, uninterrupted motion. 4. Improper use of brakes. Incorrect seat or rudder pedal adjustment, with feet in an uncomfortable position, frequently cause inadvertent application of brakes and excessive heading changes. 5. Over-controlling rudder pedals. This fault may be caused by late recognition of heading changes, tension on the controls, misinterpretation of the heading indicator, and correcting in the wrong direction, failure to appreciate changing effectiveness of rudder control as the aircraft accelerates, and other factors. If heading changes are observed and corrected instantly with small movement of the rudder pedals, swerving tendencies can be reduced. 6. Failure to maintain attitude after becoming airborne. If the pilot reacts to seat of the pants sensations when the airplane lifts off, Pitch control is guesswork. The pilot may either allow excessive pitch or apply excessive forward elevator pressure, depending on the reaction to trim changes. 7. Inadequate crosscheck. Fixations are likely during trim changes, attitude changes, gear and flap retractions, and power changes. Once an instrument or a control input is applied, continue the crosscheck and note the effect during the next crosscheck sequence. 8. Inadequate interpretation of instruments. Failure to understand instrument indications immediately indicates that further study of the maneuver is necessary. Basic instrument flight patterns. Flight patterns are basic maneuvers, flown by sole reference to the instruments rather than outside visual clues, for the purpose of practicing basic attitude flying. The patterns simulate maneuvers encountered on instrument flights, such as holding patterns, procedure turns, and approaches. After attaining a reasonable degree of proficiency in basic maneuvers, apply these skills to the various combinations of individual maneuvers. The following practice flight patterns are directly applicable to operational instrument flying. Racetrack Pattern 1. Time 3 minutes straight and level flight from A to B. Figure 741, during this interval, reduce airspeed to the holding speed appropriate for the aircraft. 2. Start a 180 degrees standard rate turn to the right at B, roll out at C on the reciprocal of the heading originally used at A. 3. Time a 1 minute straight and level flight from C to D. 4. Start a 180 degrees standard rate turn to the right at D, rolling out on the original heading. 5. Fly 1 minute on the original heading, adjusting the outbound leg so that the inbound segment is 1 minute. And start figure 741. Racetrack pattern, entire pattern and level flight. Note, this pattern is an exercise combining use of the clock with basic maneuvers. Figure 541 procedure turn. A procedure turn is a maneuver that facilitates a reversal in flight direction. A descent from an initial approach fix or assigned altitude to a permissible altitude, usually the procedure turn altitude. An interception of the inbound course at a sufficient distance allowing the aircraft to become aligned with the final approach. Procedure turn types include the 45 degrees turn, the 8260 turn, and the teardrop turn. All of these turns are normally conducted no more than 10 nautical miles, (nm), from the primary airport. The procedure turn altitude generally provides a minimum of 1,000 obstacle clearance in the procedure turn area, not necessarily within the 10 nautical miles arc around the primary airport. Turns may have to be increased or decreased but should not exceed 30 degrees of a bank angle. Standard 45 degrees procedure turn 1. Start timing at point A, usually identified on approach procedures by a fix. For example, fly outbound on a heading of 360 degrees for a given time, 2 minutes, in this example. Figure 742-2. After flying outbound for 2 minutes, point B, turn left 45 degrees to a heading of 315 degrees using a standard rate turn. After rollout and stabilizing, fly this new heading of 315 degrees for 40 seconds and the aircraft will be at the approximate position of C. TR Figure 742. Standard procedure turn, entire pattern and level flight. 3. At point C, turn 225 degrees right, using a standard rate turn, figure 542, which will provide a heading of 180 degrees. The timing is such that in a no-wind environment, the pilot will be aligned with the final approach course of 180 degrees at D wind conditions, however must be considered during the execution of the procedure turn. Compensating for wind may result in changes to outbound time, procedure turn heading and/or time and minor changes in the inbound turn. 8260 procedure turn 1. Start timing at point A, usually identified on approach procedures by a fix. For example, fly outbound on a heading of 360 degrees for 2 minutes. Figure 743, TR Figure 743. 8260 procedure turn, entire pattern and level flight. Figure 543-2. At B, enter a left standard rate turn of 80 degrees to a heading of 280 degrees. 3. At the completion of the 80 degrees turn to 280 degrees, point C immediately turn right 260 degrees, rolling out on a heading of 180 degrees, point D, and also the reciprocal of the entry heading. Teardrop patterns. There are 3 typical teardrop procedure turns. A 30 degrees, 20 degrees, and a 10 degrees teardrop pattern. The below steps indicate actions for all 3 starting on a heading of 360 degrees. Figure 744, Figure 544-1. At point B, after stabilizing on the outbound course, turn left 30 degrees to a heading of 330 degrees and time for 1 minute, 20 degrees to a heading of 340 degrees and time for 2 minutes, 10 degrees to a heading of 350 degrees and time for 3 minutes too. After the appropriate time above, point C, make a standard rate turn to the right for 30 degrees teardrop, 210 degrees to the final course heading of 180 degrees, point D, 20 degrees teardrop, 200 degrees to the final course heading of 180 degrees, point D, 10 degrees teardrop, 190 degrees to the final course heading of 180 degrees, point D. By using the different teardrop patterns, a pilot is afforded the ability to manage time more efficiently. For instance, a 10 degrees pattern for 3 minutes provides about 3 times the distance and time than a 30 degrees pattern. Pattern selection should be based upon an individual assessment of the procedure turn requirements to include wind, complexity, the individual preparedness, etc. Circling approach patterns. Pattern I1. At A, start timing for 2 minutes from A to B, reduce airspeed to approach speed. Figure 7:45, 2. At B, make a standard rate turn to the left for 45 degrees. 3. At the completion of the turn, time for 45 seconds to C. 4. At C, turn to the original heading, fly 1 minute to D, lowering the landing gear and flaps. 5. At D, turn right 180 degrees, rolling out at E on the reciprocal of the entry heading. 6. At E, enter a 500 fpm rate descent. At the end of a 500-foot descent, enter a straight constant airspeed climb, retracting gear and flaps. Figure 5:45I pattern 2 steps 1. At A, start timing for 2 minutes from A to B, reduce airspeed to approach speed. Figure 7:46, 2. At B, make a standard rate turn to the left for 45 degrees. 3. At the completion of the turn, time for 1 minute to C. 4. At C, turn right for 180 degrees to D, fly for 1/2 minutes to E, lowering the landing gear and flaps. 5. At E, turn right for 180 degrees, rolling out at F. 6. At F, enter a 500 fpm rate descent. At the end of a 500-foot descent, enter a straight constant airspeed climb, retracting gear and flaps. D. Figure 5:45-2. Chapter 7, Section 2 Airplane Basic Flight Maneuvers Using an Electronic Flight Display Introduction. The previous chapters have laid the foundation for instrument flying. The pilot's ability to use and interpret the information displayed and apply corrective action is required to maneuver the aircraft and maintain safe flight. A pilot must recognize that each aircraft make and model flown may require a different technique. Aircraft weight, speed, and configuration changes require the pilot to vary his or her technique in order to perform successful attitude instrument flying. A pilot must become familiar with all sections of the pilot's operating handbook/airplane flight manual, PO/AFM, prior to performing any flight maneuver. Chapter 7, Section 2 describes basic attitude instrument flight maneuvers and explains how to perform each one by interpreting the indications presented on the electronic flight display, EFD. In addition to normal flight maneuvers, partial panel flight is addressed. With the exception of the instrument takeoff, all flight maneuvers can be performed on partial panel with the Attitude Heading Reference System, AHRS, unit simulated or rendered inoperative. Straight and level flight pitch control. The pitch attitude of an airplane is the angle between the longitudinal axis of the airplane and the actual horizon. In level flight, the pitch attitude varies with airspeed and load. For training purposes, the latter factor can normally be disregarded in small airplanes. At a constant airspeed, there is only one specific pitch attitude for level flight. At slow cruise speeds, the level flight attitude is nose high with indications as in Figure 7:47. At fast cruise speeds, the level flight attitude is nose low. Figure 7:48, Figure 7:49 shows the indications for the attitude at normal cruise speeds. Nav 1 108.00 113.00 134.000 118.000 Com 1 123.800 118.000 Com 2 4204 100 200 16521 338 3300 XPDR 5537 IDNT LCL 23:0:34 3200 alerts cruise speed. Nav 1 108.00 113.00 Nav 2 108.00 110.60 154 200 140 4100 130 270 degrees 200 16521 338 53300 3200 level flight. The instruments that directly or indirectly indicate pitch on the primary flight display (PFD) are the attitude indicator, altimeter, vertical speed indicator, VSI, air speed indicator, ASI, and both airspeed and altitude trend indicators. Attitude indicator. The attitude indicator gives the pilot a direct indication of the pitch attitude. The increased size of the attitude display on the EFD system greatly increases situational awareness for the pilot. Most attitude indicators span the entire width of the PFD screen. The aircraft pitch attitude is controlled by changing the deflection of the elevator. As the pilot pulls back on the control yoke causing the elevator to rise, the yellow chevron begins to show a displacement up from the artificial horizon line. This is caused by the AHRS unit sensing the changing angle between the longitudinal plane of the Earth and the longitudinal axis of the aircraft. The attitude indicator displayed on the PFD screen is a representation of outside visual cues. Rather than rely on the natural horizon visible during visual flight rules, VFR, flight, the pilot must rely on the artificial horizon of the PFD screen. During normal cruise airspeed, the point of the yellow chevron, aircraft symbol, is positioned on the artificial horizon. Unlike conventional attitude indicators, the EFD attitude indicator does not allow for manipulating the position of the chevron in relationship to the artificial horizon. The position is fixed and therefore always display the pitch angle as calculated by the AHRS unit. The attitude indicator only shows pitch attitude and does not indicate altitude. A pilot should not attempt to maintain level flight using the attitude indicator alone. It is important for the pilot to understand how small displacements both up and down can affect the altitude of the aircraft. To achieve this, the pilot should practice increasing the pitch attitude incrementally to become familiar with how each degree of pitch changes the altitude. Figures 7 to 50 and 7 to 51, in both cases, the aircraft will slow and gain altitude. Nav 1 108.00 113.00 134.000 118.000 Com 1 123.800 118.000 COM 2 4000 4500 4400 4300 270 degrees 3300 XPDR 5537 IDNT LCL 23:0:34 3200 Figure 750. Pitch indications for various attitudes, 1 degree through 5 degrees. The full height of the chevron is approximately 5 degrees and provides an accurate reference for pitch adjustment. It is imperative that the pilot make the desired changes to pitch by referencing the attitude indicator and then trimming off any excess control pressures. Relieving these pressures allow for a more stabilized flight and reduces pilot workload. Once the aircraft is trimmed for level flight, the pilot must smoothly nav 1 108.00 113.00 134.000 118.000 Com 1 nav 2 108.00 110.60 123.800 118.000 Com 2 4000 4500 150 4400 140 4300 130 270 degrees 200 16521 338 53300 SPDR 5537 IDNT LCL 23:0:34 3200 Alerts Figure 551. Pitch correction for level flight, 3 bar width. And precisely manipulate the elevator control forces in order to change the pitch attitude. To master the ability to smoothly control the elevator, a pilot must develop a very light touch on the control yoke. The thumb and 2 fingers are normally sufficient to move the control yoke. The pilot should avoid gripping the yoke with a full fist. When a pilot grips the yoke with a full fist, there is a tendency to apply excess pressures, thus changing the aircraft attitude. Practice making smooth, small pitch changes both up and down until precise corrections can be made. With practice, a pilot is able to make pitch changes in 1 degree increments, smoothly controlling the attitude of the aircraft. The last step in mastering elevator control is trim. Trimming the aircraft to relieve any control pressures is essential for smooth attitude instrument flight. To accomplish this, momentarily release the control yoke. Note which way the aircraft pitch attitude wants to move. Grasp the control yoke again and then reapply the pressure to return the attitude to the previous position. Apply trim in the direction of the control pressure. Small applications of trim make large changes in the pitch attitude. Be patient and make multiple changes to trim, if necessary. Once the aircraft is in trim, relax on the control yoke as much as practicable. When pressure is held on the yoke, unconscious pressures are applied to the elevator and ailerons, which displaces the aircraft from its desired flight path. If the aircraft is in trim, in calm, non-turbulent air, a pilot should be able to release the control yoke and maintain level flight for extended periods of time. This is one of the hardest skills to learn prior to successfully flying in instrument meteorological conditions, IMC. Altimeter at constant power, any deviation from level flight, except in turbulent air, must be the result of a pitch change. If the power is constant, the altimeter gives an indirect indication of the pitch attitude in level flight. Since the altitude should remain constant when the airplane is in level flight, any deviation from the desired altitude signals the need for a pitch change. For example, if the aircraft is gaining altitude, the nose must be lowered. In the PFD, as the pitch starts to change, the altitude trend indicator on the altitude tape begins to show a change in the direction of displacement. The rate at which the trend indicator grows and the altimeter numbers change aids the pilot in determining how much of a pitch change is necessary to stop the trend. As a pilot becomes familiar with a specific aircraft's instruments, he or she learns to correlate pitch changes, altimeter tapes, and altitude trend indicators. By adding the altitude tape display and the altitude trend indicator into the scan along with the attitude indicator, a pilot starts to develop the instrument crosscheck. Partial panel flight. One important skill to practice is partial panel flight by referencing the altimeter as the primary pitch indicator. Practice controlling the pitch by referencing the altitude tape and trend indicator alone without the use of the attitude indicator. Pilots need to learn to make corrections to altitude deviations by referencing the rate of change of the altitude tape and trend indicator. When operating in IMC and in a partial panel configuration, the pilot should avoid abrupt changes to the control yoke. Reacting abruptly to altitude changes can lead to large pitch changes and thus a larger divergence from the initial altitude. When a pilot is controlling pitch by the altitude tape and altitude trend indicators alone, it is possible to over-control the aircraft by making a larger than necessary pitch correction. Over-controlling causes the pilot to move from a nose-high attitude to a nose-low attitude and vice versa. Small changes to pitch are required to ensure prompt corrective actions are taken to return the aircraft to its original altitude with less confusion. When an altitude deviation occurs, two actions need to be accomplished. First, make a smooth control input to stop the needle movement. Once the altitude tape has stopped moving, make a change to the pitch attitude to start back to the entry altitude. During instrument flight with limited instrumentation, it is imperative that only small and precise control inputs are made. Once a needle movement is indicated denoting a deviation in altitude, the pilot needs to make small control inputs to stop the deviation. Rapid control movements only compound the deviation by causing an oscillation effect. This type of oscillation can quickly cause the pilot to become disoriented and begin to fixate on the altitude. Fixation on the altimeter can lead to a loss of directional control as well as airspeed control. As a general rule of thumb, for altitude deviations less than 100 feet, utilize a pitch change of 1 degree, which equates to 1/5 of the thickness of the chevron. Small incremental pitch changes allow the performance to be evaluated and eliminate over-controlling of the aircraft. Instrumentation needs to be utilized collectively, but failures will occur that leave the pilot with only limited instrumentation. That is why partial panel flying training is important. If the pilot understands how to utilize each instrument independently, no significant change is encountered in carrying out the flight when other instruments fail. VSI tape. The VSI tape provides for an indirect indication of pitch attitude and gives the pilot a more immediate indication of a pending altitude deviation. In addition to trend information, the vertical speed also gives a rate indication. By using the VSI tape in conjunction with the altitude trend tape, a pilot has a better understanding of how much of a correction needs to be made. With practice, the pilot will learn the performance of a particular aircraft and know how much pitch change is required in order to correct for a specific rate indication. Unlike older analog VSIs, new glass panel displays have instantaneous VSIs. Older units had a lag designed into the system that was utilized to indicate rate information. The new glass panel displays utilize a digital air data computer that does not indicate a lag. Altitude changes are shown immediately and can be corrected for quickly. The VSI tape should be used to assist in determining what pitch changes are necessary to return to the desired altitude. A good rule of thumb is to use a vertical speed rate of change that is double the altitude deviation. However, at no time should the rate of change be more than the optimum rate of climb or descent for the specific aircraft being flown. For example, if the altitude is off by 200 feet from the desired altitude, then a 400 feet per minute (FPM) rate of change would be sufficient to get the aircraft back to the original. Altitude. If the altitude has changed by 700 feet, then doubling that would necessitate a 1,400 FPM change. Most aircraft are not capable of that, so restrict changes to no more than optimum climb and descent. An optimum rate of change would vary between 500 and 1,000 FPM. One error the instrument pilot encounters is overcontrolling. Overcontrolling occurs when a deviation of more than 200 FPM is indicated over the optimum rate of change. For example, an altitude deviation of 200 feet is indicated on the altimeter. A vertical speed rate of 400 feet should be indicated on the gauge. If the vertical speed rate showed 600 FPM, 200 more than optimum, the pilot would be overcontrolling the aircraft. When returning to altitude, the primary pitch instrument is the VSI tape. If any deviation from the desired vertical speed is indicated, make the appropriate pitch change using the attitude indicator. As the aircraft approaches the target altitude, the vertical speed rate can be slowed in order to capture the altitude in a more stabilized fashion. Normally within 10% of the rate of climb or descent from the target altitude, begin to slow the vertical speed rate in order to level off at the target altitude. This allows the pilot to level at the desired altitude without rapid control inputs or experiencing discomfort due to G-load. Airspeed indicator, ASI, the ASI presents an indirect indication of the pitch attitude. At a constant power setting and pitch attitude, airspeed remains constant. As the pitch attitude lowers, airspeed increases, and the nose should be raised. As the pitch attitude is increased, the nose of the aircraft raises, which results in an increase in the angle of attack as well as an increase in induced drag. The increased drag begins to slow the momentum of the aircraft, which is indicated on the ASI. The airspeed trend indicator shows a trend as to where the airspeed will be in 6 seconds. Conversely, if the nose of the aircraft should begin to fall, the angle of attack, as well as induced drag, decreases. There is a lag associated with the ASI when using it as a pitch instrument. It is not a lag associated with the construction of the ASI, but a lag associated with momentum change. Depending on the rate of momentum change, the ASI may not indicate a pitch change in a timely fashion. If the ASI is being used as the sole reference for pitch change, it may not allow for a prompt correction. However, if smooth pitch changes are executed, modern glass panel displays are capable of indicating 1-knot changes in airspeed and also capable of projecting airspeed trends. When flying by reference to flight instruments alone, it is imperative that all of the flight instruments be cross-checked for pitch control. By cross-checking all pitch-related instruments, the pilot can better visualize the aircraft attitude at all times. As previously stated, the primary instrument for pitch is the instrument that gives the pilot the most pertinent information for a specific parameter. When in level flight and maintaining a constant altitude, what instrument shows a direct indication of altitude? The only instrument that is capable of showing altitude is the altimeter. The other instruments are supporting instruments that are capable of showing a trend away from altitude, but do not directly indicate an altitude. The supporting instruments forewarn of an impending altitude deviation. With an efficient cross-check, a proficient pilot is better able to maintain altitude. Bank control. This discussion assumes the aircraft is being flown in coordinated flight, which means the longitudinal axis of the aircraft is aligned with the relative wind. On the PFD, the attitude indicator shows if the wings are level. The turn rate indicator, slip/skid indicator, and the heading indicator also indicate whether or not the aircraft is maintaining a straight, zero-bank flight path. Attitude indicator. The attitude indicator is the only instrument on the PFD that has the capability of displaying the precise bank angle of the aircraft. This is made possible by the display of the roll scale depicted as part of the attitude indicator. Figure 7-52 identifies the components that make up the attitude indicator display. Note that the top of the display is blue, representing sky, the bottom is brown, depicting dirt, and the white line separating them is the horizon. The lines parallel to the horizon line are the pitch scale, which is marked in 5-degree increments and labeled every 10 degrees. The pitch scale always remains parallel to the horizon. The curved line in the blue area is the roll scale. The triangle on the top of the scale is the zero index. The hash marks on the scale represent the degree of bank. Figure 753, the roll scale always remains in the same position relative to the horizon line. Figure 553. Attitude indicator. Figure 752. Attitude indicator. Figure 753. Attitude indicator showing a 15 degrees left bank. Figure 552. Bank interpretation with the attitude indicator. The roll pointer indicates the direction and degree of bank. Figure 753, the roll pointer is aligned with the aircraft symbol. The roll pointer indicates the angle of the lateral axis of the aircraft compared to the natural horizon. The slip/skid indicator will show if the longitudinal axis of the aircraft is aligned with the relative wind, which is coordinated flight. With the roll index and the slip/skid indicator aligned, any deflection, either right or left of the roll index, causes the aircraft to turn in that direction. With the small graduations on the roll scale, it is easy to determine the bank angle within approximately 1 degree. In coordinated flight, if the roll index is aligned with the roll pointer, the aircraft is achieving straight flight. An advantage of EFDs is the elimination of the precession error. Precession error in analog gauges is caused by forces being applied to a spinning gyro. With the new solid-state instruments, precession error has been eliminated. Since the attitude indicator is capable of showing precise pitch and bank angles, the only time that the attitude indicator is a primary instrument is when attempting to fly at a specific bank angle or pitch angle. Other times, the attitude instrument can be thought of as a control instrument. Horizontal Situation Indicator, HSI. The Horizontal Situation Indicator, HSI, is a rotating 360 degrees compass card that indicates magnetic heading. The HSI is the only instrument that is capable of showing exact headings. The magnetic compass can be used as a backup instrument in case of an HSI failure. However, due to erratic, unstable movements, it is more likely to be used as a supporting instrument. In order for the pilot to achieve the desired rate of change, it is important for him or her to understand the relationship between the rate at which the HSI changes heading displays, and the amount of bank angle required to meet that rate of change. A very small rate of heading change means the bank angle is small, and it takes more time to deviate from the desired straight flight path. A larger rate of heading change means a greater bank angle happens at a faster rate. Heading indicator. The heading indicator is the large black box with a white number that indicates the magnetic heading of the aircraft. Figure 754, the aircraft heading is displayed to the nearest degree. When this number begins to change, the pilot should be aware that straight flight is no longer being achieved. Figure 554. Slip/skid and turn rate indication. Figure 754. Slip/skid and turn rate indicator. Turn rate indicator. The turn rate indicator gives an indirect indication of bank. It is a magenta trend indicator capable of displaying half standard as well as standard rate turns to both the left and right. Figure 754, the turn indicator is capable of indicating turns up to 4 degrees per second by extending the magenta line outward from the standard rate mark. If the rate of turn has exceeded 4 degrees per second, the magenta line cannot precisely indicate where the heading will be in the next 6 seconds. The magenta line freezes and an arrowhead will be displayed. This alerts the pilot to the fact that the normal range of operation has been exceeded. Slip/skid indicator. The slip/skid indicator is the small portion of the lower segmented triangle displayed on the attitude indicator. This instrument depicts whether the aircraft's longitudinal axis is aligned with the relative wind. Figure 754, the pilot must always remember to cross-check the roll index to the roll pointer when attempting to maintain straight flight. Anytime the heading remains constant and the roll pointer and the roll index are not aligned, the aircraft is in uncoordinated flight. To make a correction, the pilot should apply rudder pressure to bring the aircraft back to coordinated flight. Power control. Power produces thrust which, with the appropriate angle of attack of the wing, overcomes the forces of gravity, drag, and inertia to determine airplane performance. Power control must be related to its effect on altitude and airspeed, since any change in power setting results in a change in the airspeed or the altitude of the airplane. At any given airspeed, the power setting determines whether the airplane is in level flight, in a climb, or in a descent. If the power is increased in straight and level flight and the airspeed held constant, the airplane climbs. If power is decreased while the airspeed is held constant, the airplane descends. On the other hand, if altitude is held constant, the power applied determines the airspeed. The relationship between altitude and airspeed determines the need for a change in pitch or power. If the airspeed is off the desired value, always check the altimeter before deciding that a power change is necessary. Think of altitude and airspeed as interchangeable. Altitude can be traded for airspeed by lowering the nose, or convert airspeed to altitude by raising the nose. If altitude is higher than desired and airspeed is low, or vice versa, a change in pitch alone may return the airplane to the desired altitude and airspeed. Figure 755, if both airspeed and altitude are high or if both are low, then a change in both pitch and power is necessary in order to return to the desired airspeed and altitude. Figure 756, for changes in airspeed in straight and level flight, pitch, bank, and power must be coordinated in order to maintain constant nav 1 108.00 113.00 134.000 118.000 com 1 nav 2 108.00 110.60 123.800 118.000 com 2 4000 130 4300 120 4200 110 270 degrees 344000 alerts 03300 PDR 5537 IDNT LCL 23:00:34 3200 figure 7 to 55. An aircraft decreasing in airspeed while gaining altitude. In this case, the pilot has decreased pitch. Nav 1 108.00 113.00 134.000 118.000 com 1 Nav 2 108.00 110.60 123.800 118.000 com 2 4000 4400 130 4300 120 4200 110 270 degrees 3300 3200 figure 756. Figure shows both an increase in speed and altitude where pitch adjustment alone is insufficient. In this situation, a reduction of power is also necessary. Altitude and heading. When power is changed to vary airspeed in straight and level flight, a single engine, propeller-driven airplane tends to change attitude around all axes of movement. Therefore, to maintain constant altitude and heading, apply various control pressures in proportion to the change in power. When power is added to increase airspeed, the pitch instruments indicate a climb unless forward elevator control pressure is applied as the airspeed changes. With an increase in power, the airplane tends to yaw and roll to the left unless counteracting aileron and rudder pressures are applied. Keeping ahead of these changes requires increasing cross-check speed, which varies with the type of airplane and its torque characteristics, the extent of power and speed change involved. Power settings. Power control and airspeed changes are much easier when approximate power settings necessary to maintain various airspeeds in straight and level flight are known in advance. However, to change airspeed by any appreciable amount, the common procedure is to underpower or overpower on initial. Power changes to accelerate the rate of airspeed change. For small speed changes, or in airplanes that decelerate or accelerate rapidly, overpowering or underpowering is not necessary. Consider the example of an airplane that requires 23 inches of mercury, Hg, to maintain a normal cruising airspeed of 120 knots, and 18 Hg to maintain an airspeed of 100 knots. The reduction in airspeed from 120 knots to 100 knots while maintaining straight and level flight is discussed below and illustrated in figures 7 to 57, 7 to 58, and 7 to 59. Instrument indications, prior to the power reduction, are shown in figure 757. The basic attitude is established and maintained on the attitude indicator. The specific pitch, bank, and power control requirements are detected on these primary instruments: altimeter, primary pitch heading indicator, primary bank airspeed indicator, primary power supporting pitch and bank instruments are shown in figure 757. Note that the supporting power instrument is the manifold pressure gauge, or tachometer if the propeller is fixed pitch. However, when a smooth power reduction to approximately 15 Hg under power is made, the manifold pressure gauge becomes the primary power instrument. Figure 758, with practice, power setting can be changed with only a brief glance at the power instrument, by sensing the movement of the throttle, the change in sound, and the changes in the feel of control pressures. 270 degrees 338.5 inset PFD figure 757. Straight and level flight, normal cruising speed. As the thrust decreases, increase the speed of the crosscheck and be ready to apply left rudder, back elevator, and aileron control pressure the instant the pitch and bank instruments show a deviation from altitude and heading. As proficiency is obtained, a pilot will learn to cross-check, interpret, and control the changes with no deviation of heading and altitude. Assuming smooth air and ideal control technique, as airspeed decreases, a proportionate increase in airplane pitch attitude is required to maintain altitude. Similarly, effective torque control means counteracting yaw with rudder pressure. As the power is reduced, the altimeter is primary for pitch, the heading indicator is primary for bank, and the manifold pressure gauge is momentarily primary for power, at 15 Hg and figure 7 to 58. Control pressure should be trimmed off as the airplane decelerates. As the airspeed approaches the desired airspeed of 100 knots, the manifold pressure is adjusted to approximately 18 Hg and becomes the supporting power instrument. The AC again becomes primary for power. Figure 759, Airspeed changes in straight and level flight. Practice of airspeed changes in straight and level flight provides an excellent means of developing increased proficiency in all three basic instrument skills and brings out some common errors to be expected during training in straight and level flight. Having learned to control the airplane in a clean configuration, minimum drag conditions, increase proficiency in crosscheck and control by practicing speed changes while extending or retracting the flaps and landing gear. While practicing, be sure to comply with the 4000-4300, 4200, 4100, XPDR. Nav 1 108.00 113.00 Nav 2 108.00 110.60 130 120 110 130 120 110 70 TOS 100 KT 270 degrees XPDR 5537 IDNT LCL 23:00:34 3200 alerts figure 558. Power control, straight and level flight, airspeed decreasing. 270 degrees XPDR 5537 IDNT LCL 23:00:34 3200 alerts figure 559. Power control, straight and level flight, reduced airspeed stabilized. Airspeed limitations specified in the PO/AFM for gear and flap operation. Sudden and exaggerated attitude changes may be necessary in order to maintain straight and level flight as the landing gear is extended and the flaps are lowered in some airplanes. The nose tends to pitch down with gear extension, and when flaps are lowered, lift increases momentarily, at partial flap settings, followed by a marked increase in drag as the flaps near maximum extension. Control technique varies according to the lift and drag characteristics of each airplane. Accordingly, knowledge of the power settings and trim changes associated with different combinations of airspeed, gear, and flap configurations reduces instrument crosscheck and interpretation problems. Figure 760, for example, assume that in straight and level flight instruments indicate 120 knots with power at 23 Hg manifold pressure /2,300 revolutions per minute, RPM, gear and flaps up. After reduction in airspeed, with gear and flaps fully extended, straight and level flight at the same altitude requires 25 Hg manifold pressure /2,500 RPM. Maximum gear extension speed is 115 knots, maximum flap extension speed is 105 knots. Airspeed reduction to 95 knots, gear and flaps down, can be made in the following manner. 1. Maintain RPM at 2500, since a high power setting is used in full drag configuration. 2. Reduce manifold pressure to 10 Hg. As the airspeed decreases, increase crosscheck speed. 3. Make trim adjustments for an increased angle of attack and decrease in torque. 4. Lower the gear at 115 knots. The nose may tend to pitch down and the rate of deceleration increases. Increase pitch attitude to maintain constant altitude and trim off some of the back elevator pressures. If full flaps are lowered at 105 knots, crosscheck, interpretation, and control must be very rapid. A simpler technique is to stabilize attitude with gear down before lowering the flaps. 5. Since 18 Hg manifold pressure holds level flight at 100 knots with the gear down, increase power smoothly to that setting as the AC shows approximately 105 knots, and retrim. The attitude indicator now shows approximately 2.5 bar width nose high in straight and level flight. 6. Actuate the flap control and simultaneously increase power to the predetermined setting, 25 Hg, for the desired airspeed, and trim off the pressures necessary to hold constant altitude and heading. The attitude indicator now shows a bar with nose low in straight and level flight at 95 knots. Trim technique. Trim control is one of the most important flight habits to cultivate. Trimming refers to relieving any control pressures that need to be applied by the pilot to the control surfaces to maintain a desired flight attitude. The desired result is for the pilot to be able to take his or her hands off the control surfaces and have the aircraft remain in the current attitude. Once the aircraft is trimmed for hands-off flight, the pilot is able to devote more time to monitoring the flight instruments and other aircraft systems. In order to trim the aircraft, apply pressure to the control surface that needs trimming and roll the trim wheel in the direction pressure is being held. Relax the pressure that is being applied to the control surface and monitor the primary instrument for that attitude. If the desired performance is achieved, fly hands off. If additional trimming is required, redo the trimming steps. An aircraft is trimmed for a specific airspeed, not pitch attitude or altitude. Anytime an aircraft changes airspeed, there is a need to retrim. For example, an aircraft is flying at 100 knots straight and level. An increase of 50 rpm causes the airspeed to increase. As the airspeed increases, additional lift is generated and the aircraft climbs. Once the additional thrust is stabilized at some higher altitude, the airspeed will again stabilize at 100 knots. This demonstrates how trim is associated with airspeed and not altitude. If the initial altitude is to be maintained, forward pressure would need to be applied to the control wheel while the trim wheel needs to be rolled forward to eliminate any control pressures. Rolling forward on the trim wheel is equal to increasing for a trimmed airspeed. Anytime the airspeed is changed, re-trimming is required. Trimming can be accomplished during any transitional period, however, prior to final trimming, the airspeed must be held constant. If the airspeed is allowed to change, the trim is not adjusted properly and the altitude varies until the airspeed for which the aircraft is trimmed is achieved. Common errors in straight and level flight. Pitch errors usually result from the following errors. 1. Improper adjustment of the yellow chevron, aircraft symbol, on the attitude indicator. Corrective action. Once the aircraft has leveled off and the airspeed has stabilized, make small corrections to the pitch attitude to achieve the desired performance. Cross-check the supporting instruments for validation. 2. Insufficient cross-check and interpretation of pitch instruments. Figure 761. Example, the airspeed indication is low. The pilot, believing a nose-high pitch attitude exists, applies forward pressure without noting that a low power setting is the cause of the airspeed discrepancy. Corrective action, increase the rate of cross-check of all the supporting flight instruments. Airspeed and altitude should be stabilized before making a control input. 3. Acceptance of deviations. Example, a pilot has an altitude range of plus or minus 100 feet according to the practical test standards for straight and level flight. When the pilot notices that the altitude has deviated by 60 feet, no correction is made because the altitude is holding steady and is within the standards. Corrective action, the pilot should cross-check the instruments and, when a deviation is noted, prompt corrective actions should be taken in order to bring the aircraft back to the desired altitude. Deviations from altitude should be expected but not accepted. 4. Over-controlling, excessive pitch changes. Example, a pilot notices a deviation in altitude. In an attempt to quickly return to altitude, the pilot makes a large pitch change. The large pitch change destabilizes the attitude and compounds the error. Corrective action. Small, smooth corrections should be made in order to recover to the desired altitude, 0.5 degree to 2 degrees depending on the severity of the deviation. Instrument flying is comprised of small corrections to maintain the aircraft attitude. When flying an IMC, a pilot should avoid making large attitude changes in order to avoid loss of aircraft control and spatial disorientation. 5. Failure to maintain pitch corrections. Pitch changes need to be made promptly and held for validation. Many times pilots make corrections and allow the pitch attitude to change due to not trimming the aircraft. It is imperative that any time a pitch change is made, the trim is readjusted in order to eliminate any control pressures that are being held. A rapid cross-check aids in avoiding any deviations from the desired pitch attitude. Example, a pilot notices a deviation in altitude. A change in the pitch attitude is accomplished but no adjustment to the trim is made. Distractions cause the pilot to slow the cross-check and an inadvertent reduction in the pressure to the control column commences. The pitch attitude then changes, thus complicating recovery to the desired altitude. Corrective action, the pilot should initiate a pitch change and then immediately trim the aircraft to relieve any control pressures. A rapid cross-check should be established in order to validate the desired performance is being achieved. 6. Fixation during cross-check. Devoting an unequal amount of time to one instrument either for interpretation or assigning too much importance to an instrument. Equal amounts of time should be spent during the cross-check to avoid an unnoticed deviation in one of the aircraft attitudes. Example, a pilot makes a correction to the pitch attitude and then devotes all of the attention to the altimeter to determine if the pitch correction is valid. During this time, no attention is paid to the heading indicator, which shows a turn to the left. Figure 762, corrective action. The pilot should monitor all instrumentation during the cross-check. Do not fixate on one instrument waiting for validation. Continue to scan all instruments to avoid allowing the aircraft to begin a deviation in another attitude. Heading errors usually result from but are not limited to the following errors. 1. Failure to cross-check the heading indicator, especially during changes in power or pitch attitude. 2. Misinterpretation of changes in heading, with resulting corrections in the wrong direction. 3. Failure to note and remember a preselected heading. 4. Failure to observe the rate of heading change and its relation to bank attitude. 5. Over-controlling in response to heading changes, especially during changes in power settings. 6. Anticipating heading changes with premature application of rudder pressure. 7. Failure to correct small heading deviations. Unless zero error in heading is the goal, a pilot will tolerate larger and larger deviations. Correction of a 1 degree error takes far less time and concentration than correction of a 20 degrees error. 8. Correcting with improper bank attitude. If correcting a 10 degrees heading error with a 20 degrees bank correction, the aircraft will roll past the desired heading before the bank is established, requiring another correction in the opposite direction. Do not multiply existing errors with errors in corrective technique. 9. Failure to note the cause of a previous heading error and thus repeating the same error. For example, the airplane is out of trim with a left wing low tendency. Repeated corrections for a slight left turn are made, yet trim is ignored. Power errors usually result from but are not limited to the following errors. 1. Failure to become familiar with the aircraft's specific power settings and pitch attitudes. 2. Abrupt use of throttle. 3. Failure to lead the airspeed when making power changes, climbs, or descents. Example, when leveling off from a descent, increase the power in order to avoid the airspeed from bleeding off due to the decrease in momentum of the aircraft. If the pilot waits to bring in the power until after the aircraft is established in the level pitch attitude, the aircraft will have already decreased below the speed desired, which will require additional adjustment in the power setting. 4. Fixation on airspeed tape or manifold pressure indications during airspeed changes, resulting in erratic control of airspeed, power, as well as pitch and bank attitudes. Trim errors usually result from the following faults. 1. Improper adjustment of seat or rudder pedals for comfortable position of legs and feet. Tension in the ankles makes it difficult to relax rudder pressures. 2. Confusion about the operation of trim devices, which differ among various airplane types. Some trim wheels are aligned appropriately with the airplane's axis, others are not. Some rotate in a direction contrary to expectations. 3. Failure to understand the principles of trim and that the aircraft is being trimmed for airspeed, not a pitch attitude. 4. Faulty sequence in trim techniques. Trim should be utilized to relieve control pressures, not to change pitch attitudes. The proper trim technique has the pilot holding the control wheel first and then trimming to relieve any control pressures. Continuous trim changes are required as the power setting is changed. Utilize the trim continuously, but in small amounts. Straight climbs and descents. Each aircraft has a specific pitch attitude and airspeed that corresponds to the most efficient climb rate for a specified weight. The PO/AFM contains the speeds that produce the desired climb. These numbers are based on maximum gross weight. Pilots must be familiar with how the speeds vary with weight so they can compensate during flight. Entry constant airspeed climb from cruise airspeed. To enter a constant airspeed climb from cruise airspeed, slowly and smoothly apply aft elevator pressure in order to raise the yellow chevron, aircraft symbol, until the tip points to the desired degree of pitch. Figure 7 to 63, hold the aft control pressure and smoothly increase the power to the climb power setting. This increase in power may be initiated either prior to initiating the pitch change or after having established the desired pitch setting. Consult the PO/AFM for specific climb power settings if anything other than a full power climb is desired. Pitch attitudes vary depending on the type of aircraft being flown. As airspeed decreases, control forces need to be increased in order to compensate for the additional elevator deflection required to maintain attitude. Utilize trim to eliminate any control pressures. By effectively using trim, the pilot is better able to maintain the desired pitch without constant attention. The pilot is thus able to devote more time to maintaining an effective scan of all instrumentation. The VSI should be utilized to monitor the performance of the aircraft. With a smooth pitch transition, the VSI tape should begin to show an immediate trend upward and stabilize on A before current procedure. Rate of climb equivalent to the pitch and power setting being utilized. Depending on current weight and atmospheric conditions, this rate will be different. This requires the pilot to be knowledgeable of how weight and atmospheric conditions affect aircraft performance. Once the aircraft is stabilized at a constant airspeed and pitch attitude, the primary flight instrument for pitch will be the AC and the primary bank instrument will be the heading indicator. The primary power instrument will be the tachometer or the manifold pressure gauge depending on the aircraft type. If the pitch attitude is correct, the airspeed should slowly decrease to the desired speed. If there is any variation in airspeed, make small pitch changes until the aircraft is stabilized at the desired speed. Any change in airspeed requires a trim adjustment. Constant airspeed climb from established airspeed. In order to enter a constant airspeed climb, first complete the airspeed reduction from cruise airspeed to climb airspeed. Maintain straight and level flight as the airspeed is reduced. The entry to the climb is similar to the entry from cruise airspeed with the exception that the power must be increased when the pitch attitude is raised. Figure 764, power added after the pitch change shows a decrease in airspeed due to the increased drag encountered. Power added prior to a pitch change causes the airspeed to increase due to the excess thrust. Constant rate climbs are very similar to the constant airspeed climbs in the way the entry is made. As power is added, smoothly apply elevator pressure to raise the yellow chevron before current procedure. To the desired pitch attitude that equates to the desired vertical speed rate. The primary instrument for pitch during the initial portion of the maneuver is the AC until the vertical speed rate stabilizes and then the VSI tape becomes primary. The AC then becomes the primary instrument for power. If any deviation from the desired vertical speed is noted, small pitch changes will be required in order to achieve the desired vertical speed. Figure 765, when making changes to compensate for deviations in performance, pitch, and power, pilot inputs need to be coordinated to maintain a stable flight attitude. For instance, if the vertical speed is lower than desired but the airspeed is correct, an increase in pitch momentarily increases the vertical speed. However, the increased drag quickly starts to degrade the airspeed if no increase in power is made. A change to any one variable mandates a coordinated change in the other. Conversely, if the airspeed is low and the pitch is high, a reduction in the pitch attitude alone may solve the problem. Lower the nose of the aircraft very slightly to see if a power reduction is necessary. Being familiar with the pitch and power settings for the aircraft aids in achieving precise attitude instrument flying. Leveling off from a climb requires a reduction in the pitch prior to reaching the desired altitude. If no change in pitch is made until reaching the desired altitude, the momentum of the aircraft causes the aircraft to continue past the desired altitude throughout the transition to a level pitch attitude. The amount of lead to be applied depends on the vertical speed rate. A higher vertical speed requires a larger lead for level off. A good rule of thumb to utilize is to lead the level off by 10% of the vertical speed rate, 1000 fpm divided by 10 equals 100 feet lead. To level off at the desired altitude, refer to the attitude display and apply smooth forward elevator pressure toward the desired level pitch attitude while monitoring the VSI and altimeter tapes. The rates should start to slow and airspeed should begin to increase. Maintain the climb power setting until the airspeed approaches the desired cruise airspeed. Continue to monitor the altimeter to maintain the desired altitude as the airspeed increases. Prior to reaching the cruise airspeed, the power must be reduced to avoid overshooting the desired speed. The amount of lead time that is required depends on the speed at which the aircraft accelerates. Utilization of the airspeed trend indicator can assist by showing how quickly the aircraft will arrive at the desired speed. To level off at climbing airspeed, lower the nose to the appropriate pitch attitude for level flight with a simultaneous reduction in power to a setting that maintains the desired speed. With a coordinated reduction in pitch and power, there should be no change in the airspeed. Descent's descending flight can be accomplished at various airspeeds and pitch attitudes by reducing power, lowering the nose to a pitch attitude lower than the level flight attitude, or adding drag. Once any of these changes have been made, the airspeed eventually stabilizes during this transitional phase. The only instrument that displays an accurate indication of pitch is the attitude indicator. Without the use of the attitude indicator, such as in partial panel flight, the AC tape, the VSI tape, and the altimeter tape shows changing values until illustrates an increase in power and the initiation of leveling off. The aircraft stabilizes at a constant airspeed and constant rate of descent. The altimeter tape continues to show a descent. Hold pitch constant and allow the aircraft to stabilize. During any change in attitude or airspeed, continuous application of trim is required to eliminate any control pressures that need to be applied to the control yoke. An increase in the scan rate during the transition is important since changes are being made to the aircraft flight path and speed. Figure 766, entry descents can be accomplished with a constant rate, constant airspeed, or a combination. The following method can accomplish any of these with or without an attitude indicator. Reduce the power to allow the aircraft to decelerate to the desired airspeed while maintaining straight and level flight. As the aircraft approaches the desired airspeed, reduce the before procedure current procedure. Power to a predetermined value. The airspeed continues to decrease below the desired airspeed unless a simultaneous reduction in pitch is performed. The primary instrument for pitch is the AC tape. If any deviation from the desired speed is noted, make small pitch corrections by referencing the attitude indicator and validate the changes made with the airspeed tape. Utilize the airspeed trend indicator to judge if the airspeed is increasing and at what rate. Remember to trim off any control pressures. The entry procedure for a constant rate descent is the same except the primary instrument for pitch is the VSI tape. The primary instrument for power is the AC. When performing a constant rate descent while maintaining a specific airspeed, coordinated use of pitch and power is required. Any change in pitch directly affects the airspeed. Conversely, any change in airspeed has a direct impact on vertical speed as long as the pitch is being held constant. Leveling off. When leveling off from a descent with the intention of returning to cruise airspeed, first start by increasing the power to cruise prior to increasing the pitch back toward the level flight attitude. A technique used to determine how soon to start the level off is to lead the level off by an altitude corresponding to 10% of the rate of descent. For example, if the aircraft is descending at 1000 fpm, start the level off 100 feet above the level off altitude. If the pitch attitude change is started late, there is a tendency to overshoot the desired altitude unless the pitch change is made with a rapid movement. Avoid making any rapid changes that could lead to control issues or spatial disorientation. Once in level pitch attitude, allow the aircraft to accelerate to the desired speed. Monitor the performance on the airspeed and altitude tapes. Make adjustments to the power in order to correct any deviations in the airspeed. Verify that the aircraft is maintaining level flight by cross-checking the altimeter tape. If deviations are noticed, make an appropriate smooth pitch change in order to arrive back at desired altitude. Any change in pitch requires a smooth coordinated change to the power setting. Monitor the airspeed in order to maintain the desired cruise airspeed. To level off at a constant airspeed, the pilot must again determine when to start to increase the pitch attitude toward the level attitude. If pitch is the only item that is changing, airspeed varies due to the increase in drag as the aircraft's pitch increases. A smooth coordinated increase in power needs to be made to a predetermined value in order to maintain speed. Trim the aircraft to relieve any control pressure that may have to be applied. Common errors in straight climbs and descents. Climbing and descending errors usually result from but are not limited to the following errors. 1. Over-controlling pitch on beginning the climb. Aircraft familiarization is the key to achieving precise attitude instrument flying. Until the pilot becomes familiar with the pitch attitudes associated with specific airspeeds, the pilot must make corrections to the initial pitch settings. Changes do not produce instantaneous and stabilized results. Patience must be maintained while the new speeds and vertical speed rates stabilize. Avoid the temptations to make a change and then rush into making another change until the first one is validated. Small changes produce more expeditious results and allow for a more stabilized flight path. Large changes to pitch and power are more difficult to control and can further complicate the recovery process. 2. Failure to increase the rate of instrument crosscheck. Anytime a pitch or power change is made, an increase in the rate a pilot crosschecks the instrument is required. A slow crosscheck can lead to deviations in other flight attitudes. 3. Failure to maintain new pitch attitudes. Once a pitch change is made to correct for a deviation, that pitch attitude must be maintained until the change is validated. Utilize trim to assist in maintaining the new pitch attitude. If the pitch is allowed to change, it is impossible to validate whether the initial pitch change was sufficient to correct the deviation. The continuous changing of the pitch attitude delays the recovery process. 4. Failure to utilize effective trim techniques. If control pressures have to be held by the pilot, validation of the initial correction is impossible if the pitch is allowed to vary. Pilots have the tendency to either apply or relax additional control pressures when manually holding pitch attitudes. Trim allows the pilot to fly without holding pressure on the control yoke. 5. Failure to learn and utilize proper power settings. Anytime a pilot is not familiar with an aircraft's specific pitch and power settings, or does not utilize them, a change in flight paths takes longer. Learn pitch and power settings in order to expedite changing the flight path. 6. Failure to cross-check both airspeed and vertical speed prior to making adjustments to pitch and/or power. It is possible that a change in one may correct a deviation in the other. 7. Uncoordinated use of pitch and power during level-offs. During level-offs, both pitch and power settings need to be made in unison in order to achieve the desired results. If pitch is increased before adding power, additional drag is generated, thereby reducing airspeed below the desired value. 8. Failure to utilize supporting pitch instruments leads to chasing the VSI. Always utilize the attitude indicator as the control instrument on which to change the pitch. 9. Failure to determine a proper lead time for level off from a climb or descent. Waiting too long can lead to overshooting the altitude. 10. Ballooning, failure to maintain forward control pressure during level off as power is increased. Additional lift is generated, causing the nose of the aircraft to pitch up. Turns, standard rate turns. The previous sections have addressed flying straight and level as well as climbs and descents. However, attitude instrument flying is not accomplished solely by flying in a straight line. At some point, the aircraft needs to be turned to maneuver along Victor Airways, Global Positioning System, GPS, courses and instrument approaches. The key to instrument flying is smooth, controlled changes to pitch and bank. Instrument flying should be a slow but deliberate process that takes the pilot from departure airport to destination airport without any radical flight maneuvers. A turn to specific heading should be made at standard rate. Standard rate is defined as a turning rate of 3 degrees per second, which yields a complete 360 degrees turn in 2 minutes. A turning rate of 3 degrees per second allows for a timely heading change, as well as allowing the pilot sufficient time to cross-check the flight instruments and avoid drastic changes to the aerodynamic forces being exerted on the aircraft. At no time should the aircraft be maneuvered faster than the pilot is comfortable cross-checking the flight instruments. Most autopilots are programmed to turn at standard rate. Establishing a standard rate turn. In order to initiate a standard rate turn, approximate the bank angle and then establish that bank angle on the attitude indicator. A rule of thumb to determine the approximate angle of bank is to use 15% of the true airspeed. A simple way to determine this amount is to divide the airspeed by 10 and add 1/2 the result. For example, at 100 knots, approximately 15 degrees of bank is required. 100 tenths equals 10 plus 5 equals 15. At 120 knots, approximately 18 degrees of bank is needed for a standard rate turn. Cross-check the turn rate indicator, located on the HSI, to determine if that bank angle is sufficient to deliver a standard rate turn. Slight modifications may need to be made to the bank angle in order to achieve the desired performance. The primary bank instrument in this case is the turn rate indicator, since the goal is to achieve a standard rate turn. The turn rate indicator is the only instrument that can specifically indicate a standard rate turn. The attitude indicator is used only to establish a bank angle, control instrument, but can be utilized as a supporting instrument by cross-checking the bank angle to determine if the bank is greater or less than what was calculated. As the aircraft rolls into the bank, the vertical component of lift begins to decrease. Figure 7 to 67, as this happens, additional lift must be generated to maintain level flight. Apply aft control pressure on the yoke sufficient to stop any altitude loss trend. With the increase in lift that needs to be generated, additional induced drag is also generated. This additional drag causes the aircraft to start to decelerate. To counteract this, apply additional thrust by adding power to the power lever. Once altitude and airspeed is being maintained, Utilize the trim wheel to eliminate any control forces that need to be held on the control column. When rolling out from a standard rate turn, the pilot needs to utilize coordinated aileron and rudder and roll out to a wing's level attitude utilizing smooth control inputs. The rollout rate should be the same as the roll-in rate in order to estimate the lead necessary to arrive at the desired heading without over or undershooting. During the transition from the turn back to straight flight, the attitude indicator becomes the primary instrument for bank. Once the wings are level, the heading indicator becomes the primary instrument for bank. As bank decreases, the vertical component increases if the pitch attitude is not decreased sufficiently to maintain level flight. An aggressive crosscheck keeps the altimeter stationary if forward control pressure is applied to the control column. As the bank angle is decreased, the pitch attitude should be decreased accordingly in order to arrive at the level pitch attitude when the aircraft reaches zero bank. Remember to utilize the trim wheel to eliminate any excess control forces that would otherwise need to be held. Common errors 1. One common error associated with standard rate turns is due to pilot inability to hold the appropriate bank angle that equates to a standard rate. The primary bank instrument during the turn is the turn rate indicator, however, the bank angle varies slightly. With an aggressive crosscheck, a pilot should be able to minimize errors arising from over or under banking. 2. Another error normally encountered during standard rate turns is inefficient or lack of adequate cross-checking. Pilots need to establish an aggressive crosscheck in order to detect and eliminate all deviations from altitude, airspeed, and bank angle during a maneuver. 3. Fixation is a major error associated with attitude instrument flying in general. Pilots training for their instrument rating tend to focus on what they perceive to be the most important task at hand and abandon their crosscheck by applying all of their attention to the turn rate indicator. A modified radial scan works well to provide the pilot with adequate scanning of all instrumentation during the maneuver. Turns to predetermined headings. Turning the aircraft is one of the most basic maneuvers that a pilot learns during initial flight training. Learning to control the aircraft, maintaining coordination, and smoothly rolling out on a desired heading are all keys to proficient attitude instrument flying. EFDs allow the pilot to better utilize all instrumentation during all phases of attitude instrument flying by consolidating all traditional instrumentation onto the PFD. The increased size of the attitude indicator, which stretches the entire width of the PFD, allows the pilot to maintain better pitch control, while the introduction of the turn rate indicator positioned directly on the compass rose aids the pilot in determining when to begin a rollout for the desired heading. When determining what bank angle to utilize when making a heading change, a general rule states that for a small heading change, do not use a bank angle that is greater than the total number of degrees of change needed. For instance, if a heading change of 20 degrees is needed, a bank angle of not more than 20 degrees is required. Another rule of thumb that better defines the bank angle is half the total number of degrees of heading change required, but never greater than standard rate. The exact bank angle that equates to a standard rate turn varies due to true airspeed. With this in mind and the angle of bank calculated, the next step is determining when to start the rollout process. For example, an aircraft begins a turn from a heading of 030 degrees to a heading of 120 degrees. With a given airspeed, a standard rate turn has yielded a 15 degrees bank. The pilot wants to begin a smooth coordinated rollout to the desired heading when the heading indicator displays approximately 112 degrees. The necessary calculations are 15 degrees bank, standard rate, divided by 2 equals 7.5 degrees 120 degrees, 7.5 degrees equals 112.5 degrees. By utilizing this technique, the pilot is better able to judge if any modifications need to be made to the amount of lead once the amount of over or undershooting is established. Time turns to headings are performed in the same fashion with an EFD as with an analog-equipped aircraft. The instrumentation used to perform this maneuver is the turn rate indicator as well as the clock. The purpose of this maneuver is to allow the pilot to gain proficiency in scanning as well as to further develop the pilot's ability to control the aircraft without standard instrumentation. Time turns become essential when controlling the aircraft with a loss of the heading indicator. This may become necessary due to a loss of the AHRS unit or the magnetometer. In any case, the magnetic compass is still available for navigation. The reason for time turns instead of magnetic compass turns is the simplicity of the maneuver. Magnetic compass turns require the pilot to take into account various errors associated with the compass. Time turns do not. Prior to initiating a turn, determine if the standard rate indication on the turn rate indicator actually delivers a 3 degrees per second turn. To accomplish this, a calibration must be made. Establish a turn in either direction at the indicated standard rate. Start the digital timer as the compass rolls past a cardinal heading. Stop the timer once the compass card rolls through another cardinal heading. Roll wings level and compute the rate of turn. If the turn rate indicator is calibrated and indicating correctly, 90 degrees of heading change should take 30 seconds. If the time taken to change heading by 90 degrees is more or less than 30 seconds, then a deflection above or below the standard rate line needs to be made to compensate for the difference. Once the calibration has been completed in one direction, proceed to the opposite direction. When both directions have been calibrated, apply the calibrated calculations to all time turns. In order to accomplish a time turn, the amount of heading change needs to be established. For a change in heading from 120 degrees to a heading of 360 degrees, the pilot calculates the difference and divides that number by 3. In this case, 120 degrees divided by 3 degrees per second equals 40 seconds. This means that it would take 40 seconds for an aircraft to change heading 120 degrees if that aircraft were held in a perfect standard rate turn. Timing for the maneuver should start as the aircraft begins rolling into the standard rate turn. Monitor all flight instruments during this maneuver. The primary pitch instrument is the altimeter. The primary power instrument is the AC, and the primary bank instrument is the turn rate indicator. Once the calculated time expires, start a smooth coordinated rollout. As long as the pilot utilizes the same rate of roll-in as rollout, the time it takes for both will not need to be included in the calculations. With practice, the pilot should level the wings on the desired heading. If any deviation has occurred, make small corrections to establish the correct heading. Compass turns. The magnetic compass is the only instrument that requires no other source of power for operation. In the event of an AHRS or magnetometer failure, the magnetic compass is the instrument the pilot uses to determine aircraft heading. For a more detailed explanation on the use of the magnetic compass, see page 721. Steep turns. For the purpose of instrument flight training, a steep turn is defined as any turn in excess of standard rate. A standard rate turn is defined as 3 degrees per second. The bank angle that equates to a turn rate of 3 degrees per second varies according to airspeed. As airspeed increases, the bank angle must be increased. The exact bank angle that equates to a standard rate turn is unimportant. Normal standard rate turn bank angles range from 10 degrees to 20 degrees. The goal of training in steep turn maneuvers is pilot proficiency in controlling the aircraft with excessive bank angles. Training in excessive bank angles challenges the pilot in honing cross-checking skills and improves altitude control throughout a wider range of flight attitudes. Although the current Instrument Flight Check Practical Test Standards, PTS, do not call for a demonstration of steep turns on the certification check flight, this does not eliminate the need for the instrument pilot in training to demonstrate proficiency to an instructor. Training in steep turns teaches the pilot to recognize and to adapt to rapidly changing aerodynamic forces that necessitate an increase in the rate of cross-checking all flight instruments. The procedures for entering, maintaining, and exiting a steep turn are the same as for shallower turns. Proficiency in instrument cross-check and interpretation is increased due to the higher aerodynamic forces and increased speed at which the forces are changing. Performing the maneuver to enter a steep turn to the left, roll into a coordinated 45 degrees bank turn to the left. An advantage that glass panel displays have over analog instrumentation is a 45 degrees bank indication on the roll scale. This additional index on the roll scale allows the pilot to precisely roll into the desired bank angle instead of having to approximate it as is necessary with analog instrumentation. Figure 768, pronounced loss of altitude is indicated on the altimeter along with the VSI tape, as well as the altitude trend indicator. Additionally, the airspeed begins to increase due to the lowered pitch attitude. It is very important to have a comprehensive scan developed prior to training in steep turns. Utilization of all of the trend indicators, as well the VSI, altimeter, and AC is essential in learning to fly steep turns by reference to instruments alone. In order to avoid a loss of altitude, the pilot begins to slowly increase back pressure on the control yoke in order to increase the pitch attitude. The pitch change required is usually no more than 3 degrees to 5 degrees, depending on the type of aircraft. As the pilot increases back pressure, the angle of attack increases, thus increasing the vertical component of lift. When a deviation in altitude is indicated, proper control force corrections need to be made. During initial training of steep turns, pilots have a tendency to overbank. Overbanking is when the bank angle exceeds 50 degrees. As the outboard wing begins to travel faster through the air, it begins to generate a greater and greater differential in lift compared to the inboard wing. As the bank angle continues to progress more and more steeply past 45 degrees, the two components of lift, vertical and horizontal, become inversely proportionate. Once the angle has exceeded 45 degrees, the horizontal component of lift is now the greater force. If altitude should continue to decrease and the pilot only applies back yoke pressure, the aircraft's turn radius begins to tighten due to the increased horizontal force. If aft control pressure continues to increase, there comes a point where the loss of the vertical component of lift and aerodynamic wing loading prohibits the nose of the aircraft from being raised. Any increase in pitch only tightens the turning radius. The key to successfully performing a steep turn by reference to instruments alone is the thorough understanding of the aerodynamics involved, as well as a quick and reliable cross-check. The pilot should utilize the trim to avoid holding control forces for any period of time. With time and practice, a flight instructor can demonstrate how to successfully fly steep turns with and without the use of trim. Once the aircraft is trimmed for the maneuver, accomplishing the maneuver is virtually a hands-off effort. This allows additional time for cross-checking and interpreting the instruments. It is imperative when correcting for a deviation in altitude, that the pilot modify the bank angle plus or minus 5 degrees in order to vary the vertical component of lift, not just adjust back pressure. These two actions should be accomplished simultaneously. During the recovery from steep turns to straight and level flight, aft control forces must be varied with the power control to arrive back at entry altitude, heading and airspeed. Steps 1. Perform clearing turns. 2. Roll left into a 45 degrees bank turn and immediately begin to increase the pitch attitude by approximately 3 degrees to 5 degrees. 3. As the bank rolls past 30 degrees, increase power to maintain the entry airspeed. 4. Apply trim to eliminate any aft control wheel forces. 5. Begin rolling out of the steep turn approximately 20 degrees prior to the desired heading. 6. Apply forward control pressure and place the pitch attitude in the level cruise pitch attitude. 7. Reduce power to the entry power setting to maintain the desired airspeed. 8. Retrim the aircraft as soon as practical or continue into a right-hand steep turn and continue from step 3. 9. Once the maneuver is complete, establish cruise flight and accomplish all appropriate checklist items. Unusual attitude recovery protection. Unusual attitudes are some of the most hazardous situations for a pilot to be in. Without proper recovery training on instrument interpretation and aircraft control, a pilot can quickly aggravate an abnormal flight attitude into a potentially fatal accident. Analog gauges require the pilot to scan between instruments to deduce the aircraft attitude. Individually, these gauges lack the necessary information needed for a successful recovery. EFDs have additional features to aid in recognition and recovery from unusual flight attitudes. The PFD displays all the flight instruments on one screen. Each instrument is superimposed over a full-screen representation of the attitude indicator. With this configuration, the pilot no longer needs to transition from one instrument to another. The new unusual attitude recovery protection allows the pilot to be able to quickly determine the aircraft's attitude and make a safe, proper, and prompt recovery. Situational awareness is increased by the introduction of the large full-width artificial horizon depicted on the PFD. This now allows for the attitude indicator to be in view during all portions of the scan. Nav 1 108.00 113.00 Nav 2 108.00 110.60 130 120 40 30 81 Problem with analog gauges is that the attitude indicator displays a complete blue or brown segment when the pitch attitude is increased toward 90 degrees nose up or nose down. With the EFDs, the attitude indicator is designed to retain a portion of both sky and land representation at all times. This improvement allows the pilot to always know the quickest way to return to the horizon. Situational awareness is greatly increased. Note, the horizon line starts moving downward at approximately 47 degrees pitch up. From this point on, the brown segment remains visible to show the pilot the quickest way to return to the level pitch attitude. Figure 769 Note, the horizon line starts moving upward at approximately 27 degrees pitch down. From this point on, the blue segment remains visible to show the pilot the quickest way to return to the level pitch attitude. Figure 770, it is imperative to understand that the white line on the attitude indicator is the horizon line. The break between the blue and brown symbols is only a reference and should not be thought of as the artificial horizon. Another important advancement is the development of the unusual attitude recovery protection that is built into the PFD software and made capable by the AHRS. In the case of a nose-high unusual attitude, the unusual attitude recovery protection displays red chevrons that point back to the horizon line. These 134.000, 118.000, COM1 123.800, 118.000, COM2, 4000, 6200, 6100, 6040, 35600, 3600, 3500, 344, 00003300, 3200, Figure 769. Unusual attitude recovery protection. Note the brown horizon line is visible at the bottom. Alerts. Nav1 108.00, 113.00, Nav2 108.00, 110.60, 180, 170, 160, 30, 30, 40, 40, 130, 134.000, 118.000, COM1 123.800, 118.000, COM2, 5400, 5300, 5200, 24800, 3600, 3500, 344, 00003300, 3200, Alerts. Figure 527. Horizon line starts moving upward at approximately 27 degrees pitch down. Chevrons are positioned at 50 degrees up on the attitude indicator. The chevrons appear when the aircraft approaches a nose-high attitude of 30 degrees. The software automatically declutters the PFD, leaving only airspeed, heading, attitude, altimeter, VSI tape, and the trend vectors. The decluttered information reappears when the pitch attitude falls below 25 degrees. For nose-low unusual attitudes, the chevrons are displayed when the pitch exceeds 15 degrees nose down. If the pitch continues to decrease, the unusual attitude recovery protection declutters the screen at 20 degrees nose down. The decluttered information reappears when the pitch increases above 15 degrees. Additionally, there are bank limits that trigger the unusual attitude protection. If the aircraft's bank increases beyond 60 degrees, a continuation of the roll index occurs to indicate the shortest direction to roll the wings back to level. At 65 degrees, the PFD declutters. All information reappears when the bank decreases below 60 degrees. In Figure 771, the aircraft has rolled past 60 degrees. Observe the white line that continues from the end of the bank index. This line appears to indicate the shortest distance back to wings level. When experiencing a failure of the AHRS unit, all unusual attitude protection is lost. The failure of the AHRS results in the loss of all heading and attitude indications on the PFD. In addition, all modes of the autopilot, except for roll and altitude hold, are lost. The following picture series represents how important this technology is in increasing situational awareness, and how critical it is in improving safety. Figure 772 shows the unusual attitude protection with valid AHRS and Air Data Computer, ADC, inputs. The bright red chevrons pointing down to the horizon indicate a nose-high unusual attitude that can be easily recognized and corrected. Note, the red chevrons point back to the level pitch attitude. The trend indicators show where the airspeed and altitude will be in 6 seconds. The trend indicator on the heading indicator shows which direction the aircraft is turning. The slip/skid indicator clearly shows if the aircraft is coordinated. This information helps the pilot determine which type of unusual attitude the aircraft has taken. Now look at Figure 7-73. The display shows the same airspeed as the picture above, however, the AHRS unit has failed. The altimeter and the VSI tape are the only clear indications that the aircraft is in a nose-high attitude. The one key instrument that is no longer present is the slip/skid indicator. There is not a standby turn coordinator installed in the aircraft for the pilot to reference. The magnetic compass indicates a heading is being maintained, however, it is not as useful as a turn coordinator or slip/skid indicator. Nav1 108.00, 113.00, Nav2 108.00, 110.60, Figure 771. Aircraft rolled past 60 degrees. Nav 1 108.00 113.00 Nav 2 108.00 110.60 134.000 118.000 Com 1 123.800 118.000 Com 2 3,440,000 Alerts Figure 528. Aircraft rolled past 60 degrees. 134.000 118.000 Com 1 123.800 118.000 Com 2 Figure 529. Unusual attitude protection with valid AHRS and ADC inputs. Nav 1 108.00 113.00 Nav 2 108.00 110.60 170 160 150 110 HDG TAS 134 KT 7 degrees Celsius Figure 530. AHRS unit failed. Figure 774 depicts an AHRS and ADC failure. In this failure scenario, there are no indications of the aircraft's attitude. The manufacturer recommends turning on the autopilot, which is simply a wing leveler. With a failure of the primary instrumentation on the PFD, the only references available are the standby instruments. The standby instrumentation consists of an analog AC attitude indicator, altimeter, and magnetic compass. There is no standby turn coordinator installed. In extreme nose-high or nose-low pitch attitudes, as well as high bank angles, the analog attitude indicator has the potential to tumble, rendering it unusable. Autopilot usage. The autopilot is equipped with inputs from a turn coordinator installed behind the MFD screen. This turn coordinator is installed solely for the use of the autopilot to facilitate the roll mode, which is simply a wing leveler. This protection is always available, barring a failure of the turn coordinator, to aid the pilot if the aircraft attains an unusual attitude. Note, the pilot is not able to gain access to the turn coordinator. This instrument is installed behind the MFD panel. Figure 775, most EFD-equipped aircraft are coming from the factory with autopilots installed. However, the purchaser of the aircraft can specify if an autopilot is to be installed. Extreme caution 134.000 118.000 Com 1 123.800 118.000 COM 2 4100 3100 3000 2900 CRS 07 1 degrees 344 0000330 XPDR 5537 IDN TLCL 23:0:34 3200 should be utilized when flying an EFD equipped aircraft without an autopilot in IMC with an AHRS and ADC failure. The autopilot should be utilized to reduce workload, which affords the pilot more time to monitor the flight. Utilization of the autopilot also decreases the chances of entry into an unusual attitude. Flying an EFD-equipped aircraft without the use of an autopilot has been shown to increase workload and decrease situational awareness for pilots first learning to flying the new system. Common errors leading to unusual attitudes. The following errors have the potential to disrupt a pilot's situational awareness and lead to unusual attitudes. 1. Improper trimming techniques. A failure to keep the aircraft trimmed for level flight at all times can turn a momentary distraction into an emergency situation if the pilot stops cross-checking. 2. Poor crew resource management, CRM skills. Failure to perform all single pilot resource management duties efficiently. A major cause of CRM-related accidents comes from the failure of the pilot to maintain an organized flight deck. Items that are being utilized for the flight portion should be neatly arranged for easy access. A disorganized flight deck can lead to a distraction that causes the pilot to cease cross-checking the instruments long enough to enter an unusual attitude. Nav 1 108.00 113.00 Nav 2 108.00 110.60 AIRFS APIELED TAS 7 degrees Celsius 134.000 118.000 Com 1 123.800 118.000 Com 2 4100 ALTFIATIULDE HDG CRS 07 1 degrees XPDR 5537 IDNT LCL 23:0:34 Figure 531. AHRS and ADC failure. 3. Fixation is displayed when a pilot focuses far too much attention on one instrument because he or she perceives something is wrong or a deviation is occurring. It is important for the instrument pilot to remember that a cross-check of several instruments for corroboration is more valuable than checking a single instrument. 4. Attempting to recover by sensory sensations other than sight. Recovery by instinct almost always leads to erroneous corrections due to the illusions that are prevalent during instrument flight. 5. Failure to practice basic attitude instrument flying. When a pilot does not fly instrument approach procedures or even basic attitude instrument flying maneuvers for long periods of time, skill levels diminish. Pilots should avoid flying an IMC if they are not proficient. They should seek a qualified instructor to receive additional instruction prior to entry into IMC. Instrument takeoff. The reason for learning to fly by reference to instruments alone is to expand a pilot's abilities to operate an aircraft in visibility less than VFR. Another valuable maneuver to learn is the instrument takeoff. This maneuver requires the pilot to maneuver the aircraft during the takeoff roll by reference to flight instruments alone with no outside visual reference. With practice, this maneuver becomes as routine as a standard rate turn. The reason behind practicing instrument takeoffs is to reduce the disorientation that can occur during the transitional phase of quickly moving the eyes from the outside references inside to the flight instruments. One EFD system currently offers what is trademarked as synthetic vision. Synthetic vision is a three-dimensional computer-generated representation of the terrain that lies ahead of the aircraft. The display shows runways as well as a depiction of the terrain features based on a GPS terrain database. Similar to a video game, the display generates a runway the pilot can maneuver down in order to maintain directional control. As long as the pilot tracks down the computer-generated runway, the aircraft remains aligned with the actual runway. Not all EFD systems have such an advanced visioning system. With all other systems, the pilot needs to revert to the standard procedures for instrument takeoffs. Each aircraft may require a modification to the maneuver, therefore, always obtain training on any new equipment to be used. In order to accomplish an instrument takeoff, the aircraft needs to be maneuvered on the centerline of the runway facing the direction of departure with the nose or tail wheel straight. Assistance from the instructor may be necessary if the pilot has been taxiing while wearing a view-limiting device. Lock the tail wheel, if so equipped, and hold the brakes firmly to prevent the aircraft from creeping. Cross-check the heading indicator on the PFD with a magnetic compass and adjust for any deviations noted on the compass card. Set the heading to the nearest 5-degree mark closest to the runway heading. This allows the pilot to quickly detect any deviations from the desired heading and allows prompt corrective actions during the takeoff roll. Using the Omnibearing Select (OBS) mode on the GPS, rotate the OBS selector until the needle points to the runway heading. This adds additional situational awareness during the takeoff roll. Smoothly apply power to generate sufficient rudder authority for directional control. Release the brakes and continue to advance the power to the takeoff setting. As soon as the brakes are released, any deviation in heading needs to be corrected immediately. Avoid using brakes to control direction as this increases the takeoff roll, as well as provides the potential of over-controlling the aircraft. Continuously cross-check the AC and the heading indicator as the aircraft accelerates. As the aircraft approaches 15 to 25 knots below the rotation speed, smoothly apply aft elevator pressure to increase the pitch attitude to the desired takeoff attitude, approximately 7 degrees for most small airplanes. With the pitch attitude held constant, continue to cross-check the flight instruments and allow the aircraft to fly off of the runway. Do not pull the aircraft off of the runway. Pulling the aircraft off of the runway imposes left-turning tendencies due to P factor, which will yaw the aircraft to the left and destabilize the takeoff. Maintain the desired pitch and bank attitudes by referencing the attitude indicator and cross-check the VSI tape for an indication of a positive rate of climb. Take note of the magenta 6-second altimeter trend indicator. The trend should show positive. Barring turbulence, all trend indications should be stabilized. The airspeed trend indicator should not be visible at this point if the airspeed is being held constant. An activation of the airspeed trend indicator shows that the pitch attitude is not being held at the desired value and therefore, the airspeed is changing. The desired performance is to be climbing at a constant airspeed and vertical speed rate. Use the AC as the primary instrument for the pitch indication. Once the aircraft has reached a safe altitude, approximately 100 feet for insufficient runway available for landing should an engine failure occur, retract the landing gear and flaps while referencing the AC and attitude indicator to maintain the desired pitch. As the configuration is changed, an increase in aft control pressure is needed in order to maintain the desired pitch attitude. Smoothly increase the aft control pressure to compensate for the change in configuration. Anticipate the changes and increase the rate of crosscheck. The airspeed tape and altitude tape increases while the VSI tape is held constant. Allow the aircraft to accelerate to the desired climb speed. Once the desired climb speed is reached, reduce the power to the climb power setting as printed in the PO/AFM. Trim the aircraft to eliminate any control pressures. Common errors in instrument takeoffs. Common errors associated with the instrument takeoff include, but are not limited to, the following: 1. Failure to perform an adequate flight deck check before the takeoff. Pilots have attempted instrument takeoff with inoperative airspeed indicators, pitot tube obstructed, controls locked, and numerous other oversights due to haste or carelessness. It is imperative to cross-check the AC as soon as possible. No airspeed is indicated until 20 knots of true airspeed is generated in some systems. 2. Improper alignment on the runway. This may result from improper brake applications, allowing the airplane to creep after alignment, or from alignment with the nosewheel or tailwheel cocked. In any case, the result is a built-in directional control problem as the takeoff starts. 3. Improper application of power. Abrupt applications of power complicate directional control. Power should be applied in a smooth and continuous manner to arrive at the takeoff power setting within approximately 3 seconds. 4. Improper use of brakes. Incorrect seat or rudder pedal adjustment, with feet in an uncomfortable position, frequently causes inadvertent application of brakes and excessive heading changes. 5. Over-controlling rudder pedals. This fault may be caused by late recognition of heading changes, tension on the controls, misinterpretation of the heading indicator, and correcting in the wrong direction, failure to appreciate changing effectiveness of rudder control as the aircraft accelerates, and other factors. If heading changes are observed and corrected instantly with small movement of the rudder pedals, swerving tendencies can be reduced. 6. Failure to maintain attitude after becoming airborne. If the pilot reacts to seat-of-the-pants sensations when the airplane lifts off, pitch control is guesswork. The pilot may either allow excessive pitch or apply excessive forward elevator pressure, depending on the reaction to trim changes. 7. Inadequate crosscheck. Fixations are likely during the trim changes, attitude changes, gear and flap retractions, and power changes. Once an instrument or a control input is applied, continue the crosscheck and note the effect control during the next crosscheck sequence. 8. Inadequate interpretation of instruments. Failure to understand instrument indications immediately indicates that further study of the maneuver is necessary. Basic instrument flight patterns. After attaining a reasonable degree of proficiency in basic maneuvers, apply these skills to the various combinations of individual maneuvers. The practice flight patterns, beginning on page 730, are directly applicable to operational instrument flying.